record. Okay, got it. All right, so here we go. All right, so we've got, we're on to page 4. We kind of went backwards a little bit because yesterday I think it's important to discuss, what radio is and where we sit on the electromagnetic spectrum, and just even what the electromagnetic spectrum is and what a wave is, because all that stuff is actually very significant when it comes to figuring out all this electrical stuff. It's kind of like, it helps to have it as a precursor to electricity. So what we're going to do first is, now that we're going to start on electricity, we're on page 4 in the printed book. So what we're going to do first is we're going to, let me undo that, go there. All right, so the first thing we're going to do is draw a couple of simple devices that we're going to use over and over and over. And the first one is a battery. And a battery has a positive terminal and a negative terminal. So this is a battery. Then we're also going to have something called a resistor, right? And very often this will be marked by the letter E for electromotive force instead of a V. A resistor. And we're going to also have this thing called a capacitor and this thing called an inductor. And notice it has a letter L. And I'm not sure why it's a letter L. It's just always been a letter L. And then we're also going to have this thing called a wire. We can make the wire any shape we want. So we are going to have several different variables, several different letters that go along with all these things. What we're going to draw is a simple circuit. And so a circuit comes from the word circle. It's kind of like a racetrack if you want to think about it. Okay, well, we've drawn a simple circuit. This has a battery. And a battery has a certain electromotive force. Electromotive force is also known as a voltage. And it's the ability to push electrons from one point to another. So does anybody know what this kind of circuit would be called?
Closed circuit.
A closed circuit.
Well, besides a closed circuit, what kind of circuit?
Short.
That would be a short circuit. That's right. Because this is just a piece of wire and the wire goes around like this and it goes right back to it. So this wire.
Wait, do you mean it's short in length, or that's what it means to short circuit?
It means it's shorted out. This is a short circuit. In other words, there's no resistance to it. It's just the battery is short circuited. It's not going through anything that's going to use its power. Eventually what will happen is that the wire will either melt or the battery will get hot and blow up. So we don't want to do that. So what we're going to add is something called a resistor. And a resistance is something's ability to object to the flow of current. All right, so the next question is, well, what's current? So what we're going to do is draw this resistor right here. And again, a resistor is something that objects to the flow of current. So, but in order to understand that, we have to understand what current is. Current, if you think about water flowing through a creek or a river, current is the flow of something, right? If you're in a drift boat and you just let it drift, you get caught in the current and you're pulled downstream. So that's called a current. And in particular, since we're dealing with electricity, and electricity is essentially a voltage, electrons, the important thing that we're going to be looking at is this thing called the electron. Okay, I'd like everyone to note that we were talking about electrons yesterday, right? We're talking about electrons way up in the atmosphere. Well, it's the same electron. They just show up in a different place. So what happens is that the electrons that we're working with are actually down in all of these components. Because if we look on a microscopic level, what we'll find is, if this is an atom and this is the nucleus, what's in the nucleus? What particles?
Protons and neutrons.
Protons and neutrons. Protons with a positive charge, neutrons with a 0 charge. and flying around the nucleus, balancing out the number of protons in different orbitals, in different orbital shapes and such. We have all these electrons zipping around at very, very high speed. And they have a negative charge such that they balance out the charge of the protons in that atom. So if we were to take a look at, let's say, copper has 29 protons and 29 electrons. So copper is a really cool atom. And why is copper such a cool atom, everybody?
Conducts electricity very well.
Conducts electricity very well. So if we were to look at copper, we would find that here's the nucleus, and flying around here, we would have lots of electrons, and some of the outer electrons would be really easy to take away and very easy to add another one. So basically, if we get an electron that floats into the area of this copper atom, we would find that that electron, as it floats in, would very easily move another one out of the way. So copper, because it's because it has these electrons floating around kind of loosely on the outside, becomes a very good conductor. Electrons that go in are matched very easily by an electron flying out with very little force. Well, if something has very little force necessary to make it do what it does, that makes it a really good conductor. It also means it has very little resistance to the flow of electrons. So since we said that resistance is the flow, resistance is the ability of something to object to the flow of current. Well, it turns out that current is letter I. Come on. Current is letter I. And current is also the flow of electrons. Well, given the fact that electrons have a negative charge, which terminal of the battery would you expect them to come out of? The plus or the minus? Notice that negative
Minus.
charge. Yeah, and in fact, they do come out of the minus. So they come out of the negative terminal of the battery. So the current goes this way from the negative terminal around to the positive terminal. But that's not how we draw it. Because somewhere around 1850, the electron had yet to be discovered. And they knew that there was this thing called current, and they picked, because of voltages, these voltages of batteries, because they could figure out how to make a battery. A battery is just basically a chemical storage system for energy. Well, they said, okay, well, it appears as though there's the plus terminal and there's the minus terminal. So let's just assume that the current flows out of the plus because plus is higher than minus, and it goes this way from the plus to the minus. So guess what, everybody? Take a wild guess what happened.
Going backwards.
They got it backwards. That's right. So we're dealing now with a mistake that occurred sometime around 1850. And unfortunately for
wait.
all of us,
Are you saying current, when we say current flows one way, are we saying it does or we pretend it does? I'm getting,
well, we now know that current comes out of the negative terminal, right? Because
Negatively charged electrons are
because
attracted to
electrons
the
are negative, and the current flow is the current is the flow of electrons. So they must come out of the negative terminal. That's the source. But what we're also saying is that somewhere around 1850, they screwed it up and everyone got used to current flowing out of the positive terminal, and nobody wanted to fix it. And besides, things go from high to low, right? I mean, that's, if you look at a mountaintop and you take your 0 point here and you're at 3,000 feet. Okay, which part of the mountain is higher, 3,000 feet or 0? Everybody, which part of the mountain's higher?
3,000.
3,000. So what happens if you throw a rock off of the top of the mountain? Where will it go? It will go to the ground, right? It's very difficult to let go of a rock and have it sucked up to the top of the mountain, right? Well, that's unfortunately the way that current actually flows, but now we don't do it that way. Because, you know, it makes more sense for things to go from high to low than from low to high. So the mistake that was made long ago lives with us today. And it is this will be one of the last times that you're asked to remember the fact that current is actually backwards from the way that we think it should be.
Doesn't that screw it up? I mean,
No.
I've always seen electrical diagrams where you assume the current flows from positive to negative. If
That's
that's
right.
not actually what's happening, isn't that going to screw something up along the way?
Nope. The only thing that can screw something up is if you have a device which is designed to function on specifically on, you know, movement of electrons, then yes, you need to know that it's actually backwards.
Isn't it just sort of a semantic error? Like, wouldn't the whole thing work properly wouldn't everything work exactly the same if they said that protons were actually negative and electrons were positive?
Well, here's the question then. What is this device called? This is actually called a resistor.
But
And that has the property of resistance, which is the ability to resist flow of electrons.
Impede electrons.
Yes. And this is measured in Greek letter ohms, named after Georg Simon Ohm. Okay, so does it matter? A resistor is just usually, if you think about it, a block of carbon. If we assume that a resistor is a block of carbon, does it matter if the current flows that way through it or that way through it? It does
No.
not. No, makes absolutely no difference. So it does not care. So a resistor does not care about the mistake that was made and which direction it's flowing. So what we're going to do is start with our circuit. We're going to draw our battery with a plus and a minus terminal. We're going to live with the mistake and connect everything with wires. And for the sake of argument, we're going to say that our wire has a resistance of 0 ohms. It's a perfect conductor. It has no resistance to the flow of electrons.
wait,
Well, so what does that leave us with? Just this resistor. Our battery has a voltage E, and the battery provides a push. This is known as it's an electromotive force, which means exactly that. Electromotive, the ability to move electrons. It's measured in volts. The value for the unit is given in the big letter V, named after Alessandro Volta, another one of the old-timey scientists who was partially responsible for figuring out that things were backwards as well. Anyway, so what we now have is we're going to say that we have a battery that has a voltage of 1 volt. That is our unit of voltage. Our battery is a 1 volt battery. Okay, so now we're going to say that our resistor has been selected and built such that its resistance is 1 ohm. Okay, so this is actually very important because this gives us our first example of Ohm's law. All right, notice that we have that omega, that's ohms, named after Ohm. Well, Ohm was pretty busy, and he came up with this thing called Ohm's law, which he said, if we have a battery of a given voltage and a resistor of a given resistance, this is the rule that connects the two. E equals I times R. We can also take this and we can make that circle again that we use for the 300 and the F and the lambda. If you're not particularly good at remembering how this thing works, you just have to make that circle and say, in this case, I'm going to have this battery, and for the sake of argument, we're going to have current flowing out of the positive side through the resistor and back to the negative side. We're going to use a big letter I, and that is measured in amps. or amperes, named after Ampere, who was another 1800s scientist. The units are given the big letter A for amps. And since in this case, this is the value we don't know, we're going to take this, we're going to cross it out, and we are left with E divided by R. So I is equal to E divided by R, which is 1 volt divided by 1 ohm. And a volt per ohm is actually an amp, so that current is 1 ampere. So just for the sake of knowing this, how big is an electron, everybody?
Little.
Really little. Yeah, really little. And in fact, there are approximately 10 to the 19th electrons per second flowing past a given point to equal 1 amp. So for reference, that's 1, 0, 0, 0. Oh, wait, I need 19 places. 0, 0, 0. And another 0. That is how many electrons are flowing past that point every second to make a 1 amp current. A lot of electrons, right? But electrons are really, really small.
So what happened in that resistor to turn them around or turn
Okay.
everything backward?
Well, let me ask this question. Let's say that instead we took this resistor and we did this with it. And we just replaced this with air. And this was, let's say, 3 inches of air. Okay, so if you take a 9-volt battery and you hold it in the air, does it suddenly arc from one terminal to the other? Do you get a lightning bolt between one side and the other of a 9-volt battery?
No.
No, and why not?
Air isn't a good conductor?
That's right. Air is actually a very good insulator because nitrogen and oxygen molecules are very stable. They don't like having electrons flying in and then flying back out. Now, if we were to take a 9-volt battery and instead we take 3 inches and we take those terminals and we stick them in a bucket of salt water, what would happen?
Depending on how salt conducts, you'd get some electricity going through it.
Salt is a very good conductor. That's why we're alive.
Oh, in water, yeah.
Yeah. That's why we're able to live, because we're basically made of salt water, and the salt is a conductive material when it's dissolved in water. So depending on what that is, that changes the value of the resistor. So if we were to take air is actually a very good insulator. If we were to take a piece of plastic or a piece of ceramic or a piece of glass or wood, if it doesn't have salt water in it, those are typically really good insulators. They're able to withstand voltages without allowing current to flow, or appreciable current to flow. So let's ask, what are some good conductors?
Silver, copper,
Yep.
aluminum.
Aluminum's
Gold.
really good. Yeah. Gold is a good one. Gold is a little expensive. Actually, gold is not as good as copper, but gold has another property, which is that it does not corrode, which means you can have gold contacts that don't wear out. But gold is also very soft. So they don't corrode, but they do, scrape off. Now, aluminum is a really good conductor, but why don't we use more aluminum for electricity?
Heats easily.
What happens?
It generates heat easily.
Well, why?
Resistance to the electricity.
Yeah, except aluminum actually, if you treat it properly, is actually an excellent conductor that with very, very low resistance. So why don't we use more aluminum? Has anyone ever worked aluminum?
Yes.
Difficult.
Is it because of the oxidation or something?
Yeah, aluminum is also a very reactive metal and it oxidizes very fast and it forms a black layer on the surface. And that black layer is not conductive. So the center of the aluminum is conductive, but the surface is not. And what happens is if you try to put two pieces of aluminum wire together, let's say like this, and you twist them together, what'll happen is that wherever they're not immediately touching, you'll get a layer of oxidation that forms, which is not conductive. And then what'll happen is you'll have a high resistance forming. And this is where we get to our next part of it. Okay, so we said that what's Ohm's law, everybody? E equals
I times R.
I times R. Okay, now we have another part of Ohm's law, which is the power equation. P is equal to I times E. And we can actually substitute the E equals I times R into this and make several different power equations. We can make it into V squared divided by R or I squared R. Or I squared times R. Go ahead.
How is E different from P?
P is power.
How is E not power?
What is E? What were
How
the
is-
units?
Isn't E power?
Nope. What was E again? Electromotive
Volts.
electromotive
power?
force.
Electromotive force times volts.
So electromotive force is the ability to push electrons. P is power, and it's a combination of how hard you're pushing versus how much you're successfully able to push. And the cool thing about power is that power is the same thing that you do when you, for instance, rub your hands together and you make heat. So now the question is, could I take my hands and instead of rubbing my hands together, could I take two mechanical hands and connect them to an electric motor and cams and have my hands, my fake hands being turned by an electric motor caused to generate heat? And the answer is yes, because power is measured in watts and it doesn't matter what form it is because energy has to be what, everybody? Remember from
Conserve.
yesterday?
Conserve.
Neither
Conserve,
created
that's
nor
right.
destroyed.
That's right, neither created nor destroyed. So basically, if you have electrical power, that's the same as heat power, that's the same as motion, that's the same as chemical power being generated, that's the same as power being dissipated in a wire and heating things up. Power is power is power, and energy is energy is energy. And it doesn't matter what form it is, it has to show up somewhere. So the cool thing about it is that if we have,
So resistance would produce heat.
yep, and in fact, we're going to do that right now. So we're going to take our 1 volt battery and we're going to have it make current flow through here because we have our plus and our minus, and our current's going to go this way. And we have our resistor, which we're going to say is 1 ohm. And we're going to, what's Ohm's law again? E equals
1 times R.
I times R. Okay. And we have our E right there. And we have our R right here. We can make our circle EIR like that. And the one that we don't know is our I. So we cross that out. I is equal to E divided by R right there. It's equal to 1 divided by 1. Equals 1 amp. Okay, now we're going to take these new values. We're going to say I is equal to 1 amp. We're going to take these new values and plug it into the other equation of Ohm's law. What was that other equation, everybody?
P
Yep.
equals I times.
Everybody likes pie, right? Everybody likes to eat pie. So we're going to actually use that to draw this pie. So right there's our pie. And what don't we know here? We don't know our power. So we're going to cross that out. Now we have I times E is equal to 1 amp from right there. And our E is 1 volt is equal to 1 volt times an amp. By definition, a volt times an amp is a watt if they're in phase. That is 1 watt of power. And because a resistor fights back against the flow of current, the act of it fighting back generates heat. So what will happen to that 1 watt in that resistor? What will
Dissipated as heat.
It'll be dissipated as heat. You will have a 1 watt heater. Okay, so now we're going to take the next logical step of this. We're going to have a 120 volt battery because we can do that. And we're going to take I didn't want to do that. Let's just finish off our circuit. Okay, we're going to take a resistor that is, let's say 5 ohms. Now, you know what? Let's make it 10. I like 10. Okay. Somebody tell me what to do. What is the first thing that we don't know?
Current.
We don't know the current. That's right. So here's our current. And what is Ohm's law again?
Current is equal to voltage divided by resistor.
Yeah, but let's do it the other way. E equals
I times R.
I times R. That is, and I believe in knowing just a couple of equations. I made it all the way through college this way. You can always go back to the root equations that you know. And to be totally honest, I work in factory automation and I work in power stuff and moving voltages around and all kinds of different voltages and currents. 90% of all the things that I come up with and have to figure out are Ohm's law. Even like at work, 90% of problems electrically are related to Ohm's law. So if there's 2 things that you remember from all of this, one is Ohm's law and the other is the other part of Ohm's law. All right. So
The
You mean,
voltage divider equation, something like that.
right. So we're going to rearrange it. We're going to make E, I, R like that. And what's the thing we don't know? We don't know our current. So I is equal to E divided by R. And what's the value of our E, which is our voltage? 120 volts. And what's our R, which is our current?
10
10
ohm.
ohms. And a volt per ohm is an amp. So that's 12 amps. So that is our current. Okay. We are well on our way. So what's the next part of Ohm's law?
is it the
everybody-
P line?
Power.
Everybody likes to eat pie. Here we go. Now we're going to figure out how much power is being dissipated. Okay, so what's the thing that we don't know again?
Right.
Well, we know our current because we already just calculated it.
Power.
We don't know our power.
Oh.
The power is equal to I times E. And that's 12 amps times 120 volts. And how much do we have from that? 1,440 watts. Okay, so
Oh,
where-
okay.
where is all that wattage coming out?
The resistor.
In the resistor. So what is this device known as? You might have one in your house.
Heater.
That's a space heater. If it's in an oven, that's an oven heating element. If it's in a toaster, that's a toaster. If it's in a hot water heater, this is a hot water heating element. Yeah, it could be anything that makes a lot of that generates a lot of power as heat. It's an electrical resistance heater. So now there's a couple of things that we're going to learn from this. How much energy or how much power does the battery have to make? If the resistor is consuming 1,440 watts, how much energy or how much power does the battery have to be making?
Ideal conditions the same.
The same, that's right. We assumed perfect wire, which has no resistance. So this has to be making 1,440 watts because, everyone, the power has to go
That will
somewhere,
produce the heat for the device. to
right?
function.
You can't make it from it. You can't make it from nothing, and you can't make it disappear. So basically what that means is that the power has to go somewhere and it has to be generated by something, and it
Right.
has to be equal. So
Okay.
go ahead.
So to get this 1,440 watts, you had to have a generator, a battery that was capable of one.
That's right. That
41.
actually, okay. So now let's say that instead we were to replace this battery because this battery has a voltage. This is actually a good time to bring this up. This battery has a voltage of 120 volts. So by virtue of it being a battery, does the voltage ever change?
Yes.
No,
No, it does not. I mean, it does as it gets weaker, but you know, a 120 volt battery, if we were to measure this voltage over time, voltage versus time, it would be at 120 volts. And it would always stay at 120 volts. So would current switch direction, or would it always go the same way?
Same.
It'll always go the same way. Okay, remember yesterday we drew sine waves and we spent a little time on sine waves, and there was a mention of something called RMS. And RMS was the ability of a sine wave to produce the same amount of power as a DC voltage. And we drew it something like this.
Wasn't it the average of the current?
No, it was the average power generated by that voltage across a given resistor. That is what RMS is. It's an equivalent voltage that produces the same average power as a DC voltage. So that, if you remember right, this was a voltage that peaked at a plus 170 and went all the way down to minus 170. That was a sine wave, an AC sine wave. This is alternating current, because when the voltage is on the positive side, we're going to remove this here, and we're going to replace this now with something that looks like this, which is a sine wave, right? There's that picture of a sine wave again. And sometimes during this positive part that I drew, what you'll have is your positive part will make it so that your plus is here and your minus is here. During that time, which way does the current flow?
Positive to minus.
That's right. It flows this way out of the top of the battery. Okay, but now we're going to look at the other side down here. Can everyone see that yellow mark?
No.
Yes.
Oh, yeah.
Okay, when that is true, what happens to the battery voltage?
Reverses
It
course.
reverses, okay? And the current is no longer flowing that way, is it? Which way does the current flow? Still flows out of the positive, but we have a new positive, right? Is the positive at the top or the bottom of the battery? Top or the bottom of the battery?
Bottom.
Bottom. So the current is now flowing this way. Now, the important thing is, does the resistor care?
No.
Nope. Resistor doesn't care which way the voltage is flowing, which way the current is flowing. Doesn't matter. So as far as the resistor is concerned, the power still gets there. We have now selected a new battery, but it's an AC battery, which has a peak at plus 170 and a negative peak at negative 170, which produces the same power as 120 volt DC. And this is known as our power coming out of our wall. This is 120 VAC. And remember that it's RMS. But basically, we just call that 120 volts. When you stick your meter into your wall socket, you will find that if it's an RMS reading meter, it will say your voltage is 120 volts. But you have to know that it goes all the way up to here and all the way down to here. But it produces the same equivalent power as 120 volts DC would. So if we were to use that power supply, coming out of the wall, how much power would we actually get out of our resistor? The answer is exactly the same. It would be the average power, but we're still basically looking at it over time, and we'd still get 1440 watts. So the cool thing about dealing with RMS AC voltages is that we don't really care about the time average over, the average, the fact that it goes up and down and up and down. We just care what the average is, and the average is exactly the same. We still get the same average 1440 watts.
So when my power supply is reading out 113, 117, it's giving me an RMS value.
Yep. If you were to put that on an oscilloscope, you would see about 166 volts positive and 166 minus. And you'd actually have it crossing the 0 point here and here and here and here and here. If you were to look at your wall voltage, that's what you would see.
It would be 60. It would cross 60 times a second or 120 times.
It would cross 120 times a second because it's 60 hertz, right? So everybody, the wall voltage that you have has a frequency of 60 hertz in the United States. In Europe and South America, it's actually 50 hertz, but it's not 120 volts. It's actually 220 volts. So we have 120 volts, 60 hertz. In Europe and South America, they have 220 volts, 50 hertz, which is why if you look at your computer power supply, you will see that your computer power supply has an input voltage range of 90 to 264 volts AC. Now, why on earth would anybody do that?
To be able to sell one product worldwide.
Exactly. If you only have to make one of them, you can sell it everywhere and not have to worry about the voltage. So they have a very wide range power supply. And
Asia is 220 as well.
actually, some parts of Asia, like Japan, are 100 volts at 50 hertz. And some places are 240 at
Working with the
50.
220 inherently more dangerous wherever it is.
Yeah, I guess. I mean, either one will kill you.
What are the benefits?
Okay, so the benefits.
Population.
Transmission loss.
Okay, yes. Okay, so let's take a look at, we're going to have, okay, we're going to have two different power supplies. Right? We're going to have two different AC power supplies. And we're going to go to this. We're going to make essentially a short circuit. Okay. This is actually a really good question. And we're going to say that this has a resistance of 0.01 ohms. So it's no longer a perfect wire. And at the end of this, what we're going to do is we're going to make a resistor. The resistor is the load, the device that's supposed to be using power. In this case, this is my house. This is the end user of the power. All right. Everybody good with that so far?
Yeah.
Okay. So let us say that this is the end user at the house, and this is a 120 volt system, and this is a 240 volt system. Notice I doubled it just to be convenient. And this is actually AC, and this is AC. And at any given point in time, the people in the house are using, let's say, 1200 watts. Okay, so let's now ignore this right here, right? We're just going to ignore that. So at 1200 watts, at 240 volts, and we'll call this 120 volts AC. We're going to figure out what the current has to be. Ready? Okay, somebody give me Ohm's law. Notice I'm drilling you guys on this.
E times IR.
E equals I times R. Okay, we have 120 volts. This is our voltage. That's 120 is equal to I times R. But okay, well, that's not really going to work, is it? Because we have two things we don't know. We don't know the current and we don't know the resistance. So we're going to have to use something else. What's the other one that we can use?
The other part of Ohm's law.
Yep, which is
E equals I times E.
P equals I times E. Okay, and we do know the power, don't we? 1200 is equal to I times 120, and what does I equal then?
100.
I hope it's 10.
And
I is 10 amps. Okay, so now we're going to do the same thing down here. P is equal to I times E. And we have 1200 watts again. It's equal to I times, but in this case, it's 240. So what's our current?
5 amps.
5 amps. Okay. Now we have 10 amps going through the top circuit, right? Okay. And we have 5 amps going through this one. Here we go. What is the voltage drop right here? We're going to assume that this is now a resistor, and this is a resistor. This is the wire. Okay, so for the upper one, we're going to do Ohm's law. Ohm's law again. E equals
I times R.
I times R. Okay, well, we have our I is 10 and our R is 0.01 is equal to 0.1 volts. Okay, to make sure that we have 120 volts over here, we now have a loss of 1/10 of a volt. So what does that mean that this 120 volt circuit actually has to be?
Slightly higher.
It actually has to be 120.1 volts. Okay, so now let's go to the bottom one. We're going to do Ohm's law again. E equals I times R. Okay, so now, but instead we have 5 amps times 0.01 is equal to 0.05 volts, which means that now we have 240.05 volts. Okay, so notice we don't have to boost our voltage quite as much down below. We started higher in the first place, and we don't have to boost it as much. And now we're going to get to the really important part. Okay, so now we have that circuit again. We're going to do the power calculation. P is equal to what, everybody?
I times E.
I times E. Okay, so what is it for this thing up here? What's our current that's marked up there?
Correct.
How many amps?
10.
10 amps. And what is the voltage that we lost in there?
0.1 volts.
0.1 volts is equal to 1 watt. Okay, how about down here? Power is equal to I times E. It's equal to 5 amps times, but our voltage is 0.05. It's equal to 0.25 watts. So by jacking up the power, or by jacking up the voltage, what has happened to our power dissipation in the wire?
A lot less.
It's a lot less. Okay, and now let's take a look at what happens if we were to instead look at the same situation, because the people in the house don't really care, do they? All they know is that they can run the microwave oven. So who actually cares?
Power company.
The power company. That's
The
exactly
line
right.
workers who might
The line-
get fried.
Well, they're going to get fried anyway. They know how, assume they know how to operate safely. But what really matters is that now you look at this difference in power loss, right? What does that power loss come out as?
Heat.
Heat. Okay, so if you're the power company, would you rather sell power to your customer or heat up the wires?
Sell power.
Bell
You'd
power.
rather sell power. That's right. So now let's instead take a look at this 120 volts and convert this to 120,000 volts. So now we've gone up in voltage by a factor of 1,000, right? And right here, before it gets to the customer, we use a transformer to change the voltage down to something that they can use. So we deliver the voltage to that transformer, which is very, very efficient at 120,000 volts. And the power is conserved, which basically means that we have dropped our current by a factor of 1,000, which means we've dropped our power dissipation by a factor of 1,000,000, which is really good because instead of heating up the wires, we can actually sell the power, which is exactly what we want to do.
Bonneville has an amazing scenario in the Dows where the transmission is in DC voltage, millions of volts. Yep. And then they have a converter, an amazing transformer facility that's right out of Star Wars that converts it to AC.
Yep, I've seen that. And actually at Bonneville, they have 1 million megavolts DC. They have a plus wire and a minus wire that are separated by a very big distance. And they can send an immense amount of power at very low current. And that's exactly why you would do that. So now, here's the next question. We've established that it's easier to send power at really high voltages, and we're actually going to get to transformers in just a little bit once we do inductors. Okay, so now we're going to draw our heater again. This is our heater circuit, 120 volts. Is it AC or DC, everybody?
AC.
AC. Although we could do it off of DC, but we're not going to. So we're going to draw our heater circuit again, which had a 10 ohm resistor, and it was drawing 1,440 watts. Okay, now we're going to have a little bit of a problem. We're going to have a little bit of a problem in that something happened in our resistor and it developed a short circuit across half of it. So now the resistor looks like this. And our new resistance is 5 ohms. Okay, so let's go through the power calculations again. Ready? We have to find the current. How do we find our current? Somebody give me Ohm's law again.
E times IR.
E equals I times R, right? Okay, and we don't know our current. So we don't know our current. I is equal to E divided by R is equal to 120 divided by 5, and that's volts, and ohms is 24 amps. Okay, what's the other part of our Ohm's law calculation? The power calculation,
I.
everybody? Yep, P is equal to I times E. P-I-E. We don't know our power now. P is equal to 24 amps times 120 volts. Somebody tell me that's 2,880 watts. Okay, so what problems do we have here?
You need one hell of a resistor.
Well, yeah, well, but you can't change the resistor. In other words, there was an internal fault in the resistor that caused it to become shorted out. So you can't change the resistor. So name some problems. This current that's flowing through the wire is now how much current? That is now 24 amps.
Can produce a lot of heat.
Okay. So if that wire is 24 amps, how is this whole thing being run? How do you plug it in, everybody?
Well, something.
Well, I hope you have a wall outlet, right? And so how much current has to flow from the breaker panel through the wall to your wall outlet?
24 amps.
20 volts.
24 amps. Okay. How much current does the wall outlet have to be able to source then?
24 amps.
24 amps. How about the plug that you plugged into it?
Same.
Same. How about the wire that's connecting the plug to your space heater?
The same.
Same thing. Okay. So what's going to give out first?
I mean, if the circuit breaker is rated.
Well,
rated-
okay. You just
Or
brought
the
it up.
wire.
Okay. What if you have no circuit breaker here? What's going to give out first?
The wire.
I don't know. Who knows?
Yeah.
What?
Yeah, we don't
Okay.
know.
So you don't know. And what are the things that are going to happen as things start to overheat?
Melt,
You can melt. What else can happen?
Fire.
burn.
You set your house on fire. A lot of people run this is why you should never run a cord underneath a rug, because the cord can get hot without melting and then it can set the rug on fire. The other thing that can happen is the outlet might say, okay, well, I can temporarily handle it and the cord can handle it. And how's the power getting from your circuit breaker, your breaker panel, to the receptacle?
House wiring.
House wiring. And what can happen when your house wiring gets hot?
Combustible.
It'll burn your house down. That's right. Okay, so this is the basis of electrical safety. So we can add something right here. We can add a couple of different things, actually. There's our resistor, which is now a 5 ohm resistor, which is now running 2880 watts. So this thing will probably get very, very hot for a little bit of time. And we'll start pulling 24 amps. So we can basically put in a device which is now calibrated to carry only a certain amount of current. And in industry, we call this an OCPD, which is an overcurrent protective device, also known as a fuse or a circuit breaker. And we pick a fuse or a circuit breaker to be able to handle a certain amount of current and to trip or blow or melt, depending on what it is, above a certain amount of current. So if we picked our circuit breaker to trip at 15 amps, normally the space heater would be using 12 amps of current. Now it's using 24. What would happen to this circuit breaker?
Boom.
It would trip and it would keep your house from burning down, right? And then you'd say, oh, well, I wonder what's going on. And you go and reset the breaker. And what would happen the next time you ran it?
It should
Same
blow
thing.
again.
It would trip again, right? So now if you had a fuse, the fuse would melt. You'd replace the fuse, you'd see that it melted again and that you had some kind of problem somewhere. So basically, this is a sacrificial device which sacrifices itself to keep your house from burning down. And that's known as a fuse, which is why whenever we have a piece of electronic gear, we put in a fuse, because it's much better to just melt the fuse than it is to damage the equipment or to burn your house down. Okay, so now we've covered overcurrent protection. And let's see, how about a 5-minute break? And when we come back, we'll talk more about what comes next, which are more interesting devices, such as capacitors and inductors and transformers and things like that. Does that work?
It works.
Okay. 5-minute break.
I'll do the 5-minute break. You should have been here for this. Never mind.
Yeah. Well. For people who's never had basic. Crash course.
Hello, everyone. Anyone with any questions?
No.
No, that's good.
Hey, Scott,
Yeah.
just a quick question. I was wondering if you could explain the connection between what we just talked about with the radio thing we're trying to learn. How does the two connect?
Well, okay, if you basically, okay, power is power is power, right? If you're using a transmitter, you're using that's using a battery. If you're using a receiver, you're using a battery. You're using something that's plugged into the wall. You're using a power supply. They're all one and the same. You have to understand the power side of things in order to understand how it translates into generating power. And good morning, Haisu. Is it Haisu?
Yes, hi Sue. So when we're using radios, does it mean like we're generating power? So we're trying to relate this kind of generation with how our appliances are.
Yep.
Rated.
I mean, basically, you're converting one form of power to another,
Hmm.
right?
Yeah.
It's coming in through the wall, or being stored in a battery. And that will tell you, basically the capacity of a battery is measured in watt hours or amp hours or volt amp hours. That's capacity. It's basically it'll store, let's say you have a battery that's 100 watt hours. That means you can dissipate 1 watt for 100 hours or 100 watts for 1 hour.
Mm-hmm.
So it's all math at that point.
Okay, thanks.
So by the way, did you see the note on the Ducks Club? Did you talk to Dean?
I have not.
Okay.
But I will.
So next Tuesday we have our meetings are still on Zoom, but I don't know if we over at the University Club, my daughter's the president, by the way. She's got her extra class license. And anyway, we wrote a grant proposal and we got a $26,000 grant for station equipment.
Wow.
So we will be building station equipment and hopefully getting a space. I hope, and maybe some, I look around and I see Prince Lucian Campbell Hall, 12 stories high with antenna towers on top already.
Yeah,
And
that's my building, PL6.
Is it? Oh, well, that's really good. would you like to put in a good word for us?
Oh, of course, yes.
Because we've been talking about, places on campus, and there's already towers up there. And if we can get a room up there to put a station up there, because nobody wants to be in that building 12 stories up. I mean, right?
Mhm. Yeah.
Scott, what do you do for a job?
I build factory automation equipment. Yeah, I build machinery for a living, and I go all over the world and install it. And
Would that make you a professional engineer?
I am not a PE. I mean, I'm an engineer by profession, but I do not have a PE license. It is something that I've thought about and never done, just because, I have a master's in electrical engineering, and unlike mechanical engineers or civil engineers, you do a lot of, government projects and things like that. Really, the time that you would need a PE license is if you sign off on official projects, like a building heating system or something like that, or city water system or a dam. But if you're just building, like if you're an electrical engineer, if you work for a power company, because it's being done for the city, a public interest, you would need a PE license to be able to sign off on projects. But just, building equipment that's going to go into a factory, they just want to see that it's designed properly. So.
I just asked, I have a friend who's a PE out at Monaco.
Yeah, and that's probably the same reason, because it's, it's being designed for like individuals, electrical or mechanical PE.
Mechanical.
Yeah, and again, that's because it's, something that I think it's a vehicle that's going to be out on public roads. It probably has something to do with that.
Yeah, they do a lot of structural work with the slide outs and stuff.
Yeah.
Where it all has to be certified to be on the road and stuff.
Yeah, and we don't typically have to do that. We just have to, show that, like, but I actually have like a UL 508 certification that I passed an exam for, which basically means I know how to implement UL 508, which is a certification process for panel building and, picking the right electrical components and making sure that things are overcurrent protected properly and stuff like that. Because we're a self-certifying UL 508 panel shop. Okay, everybody get ready to get going again?
Yep.
So we have not been covering the examples that are being shown in the book. The reason being that the stuff that we're doing, if you remember those two equations, we don't really need to go through the examples unless people want to, because it's all just applications of E equals I times R and P equals I times E. And what I found was nice about school was that, you could remember, you could memorize things if you wanted to, but really all you really had to do was memorize. All you really had to do was know a couple of basic equations, and then you didn't have to memorize everything else. You could always just move things around and use those equations to figure out the problem. So when it comes time to studying, what I recommend doing is, for instance, there's like a question, how much power is being used in a circuit when the applied voltage is 13.8 volts and the current is 10 amps? Well, they ask for power, and you have voltage and current, so P equals I times E. You now know the equation. We've gone through it enough times to know that you now know how to apply it. Okay, yeah.
Well, my mind is not where yours is. I'm confusing E and P, and E is always going to be measured in volts and P
Always.
in watts.
Yep, they're totally different, fundamentally completely different things.
But E is always going to be measured in volts and P is always going to be measured in watts.
Correct.
Okay.
Yep. And E is what?
Electromotive force.
Electromotive force, and P, watts.
P, watts.
And what is that a measure of?
It's power.
That's power.
Because I was assuming, volts and watts are both power, but they're
not. They're not.
Okay,
Okay, a power is energy per unit time. That is the definition of power.
Like,
Energy, what?
right?
What did you say?
Power is energy per unit time.
unit of time.
Yep. Which we think of as a second.
And how are volts not?
A volt is just a volt. It's how much push something has available to it. And they're totally different.
Mm.
So I mean, energy
Like
is measured.
potential, volt is more potential.
Well, voltage is a measure of potential. It's
The
electromotive force.
The garden hose example was helpful, I think.
Yeah, well, it's the question of, let's say that you have a, here we go. This is the application. Let's say you have a really big block that's sitting on the ground. Let's say this is a granite block, right? And it's sitting on the ground, and the ground is basically a driveway, which is, rock. So you're basically pushing rock on rock,
Okay.
right? That's the resistance if you try to push. So let's say that you're standing here.
So
and
the
you're-
resistance is the gravel.
Right, yeah. And the resistance is how much it's pushing back. So let's say that now you lean against this, right? And you try to make it move. How hard you push is the voltage. Right? It's essentially a force. It's electromotive force. Except that in this case, we're trying to move a really big block of gravel or a really big block of granite over the ground. All right. So what can you do to move this block? It's not budging. You have two different options. You have a few different options. What can you do?
Increase voltage.
Right. You can
Push
go
harder.
get a couple of friends, right? You have another friend who's here who helps you push. And when you do that, what are you doing?
Increasing the force.
Increasing the force because you're having more people push. You now have more push.
You
You could also go to
decrease
the gym. You
resistance.
could also go to the gym and work out and, bulk up a little bit. That would be another way to do it. Right? Now,
Or decrease the resistance.
or decrease the resistance. So what would be a good way to decrease the resistance?
Water, logs, grease.
Yeah, you could take it, and instead you could, if you manage to get it up in the air, you could take it and you could put rollers under it. In which case you wouldn't have to push as hard to get motion. So basically you can change the resistance or you can change the push. So this is the voltage. This right here is the resistance. And the fact that it moves, if it moves easier, this is your current. The faster it goes, the more successful you were.
And current would just be the rate at which it rolls now
Yep.
that you have changed voltage and resistance.
Correct.
Okay, by that logic, amps or current are the more dangerous thing than voltage.
That is true. Although, okay, so let me ask this question. All right, so here's me. This is actually a pretty, good representation of what I actually look like. Okay, so let's say that I have two hands here and I grab one electrode, which is a plus, and one that's a minus. And I hook this up to a 1.5 volt battery.
You're now a resistor.
Yeah, I'm a resistor, right? Well, I'm a resistor, but I'm also full of salt water. But fortunately, I have this thing called skin. So let me say that my resistance is 40 k ohms, which is pretty reasonable.
40 what?
40 k ohms. We're going to get to that, right? We're going to get to that right now. Okay, so we're going to have units. We're going to start with our 0, which is just our unit. In this case, it's an ohm. And we're going to have 1,000. That's represented by the little letter K, which is kilo. And then there's a million, which is represented by the big letter M. And then we can also put 0.001, which is milli. and 0.000001, which is micro. And then we can get bigger, which is giga, and 0.0000001, which is nano, and 0.00000000001, which is pico. Now, if you count zeros, you'll see that this is 10 to the 9th power because it's 10 times 10 times 10 times 10 times 10 times 10, like 9 times. This is 10 to the 3rd power because it's 10 times 10 times 10. This is 10 to the 6th power. By convention, this is 1/10 times 1/10 by 1/10. So this is 10 to the -3 power, 10 to the -6, 10 to the -9, 10 to the -12. So the reason we do that is because we don't want to carry all those extra zeros. They become kind of a pain in the neck to deal with. So if I have a resistance of 40K ohms, that's 40,000 ohms. I can also write it as 40K ohms. So now we're going to do Ohm's law on this. E is equal to I times R. E, I, R, like this. And we don't know our current. So I is equal to E divided by R, which is 1.5 divided by 40,000, which is equal to, I have to grab my calculator for this. Let's see, 2.5, 3.75. So that's 37.5 divided by a million, which is 0.000375 amps, or 375 by moving this 1, 2, 3, 4, 5, 6, 37.5 microamps. So I will feel nothing from that. I won't feel any effect of 37.5 microamps. But now let us take this and let us put me in the workplace and say that I'm stupid enough to be working on something and I see 2 lines of voltage that I'm working on and they are 480 volts RMS. Okay, so 480 volts RMS. We're going to do the same equation, E, I, R. Again, we don't know our current. I is equal to E divided by R is now equal to 480 divided by 40,000 is equal to, let's see, 1, 2, 4.8 over 400 is equal to 1.2 over 100 is equal to 0.012 amps. 1, 2, 3, or 12 milliamps. So we just played around with our decimal places a little bit. 1.2 divided by 100 is 0.012. We slide the decimal place over 3 places, and that becomes milli. And now we have 12 milliamps. All right, anyone take a guess as to what 12 milliamps might do to me?
Make your shorts wet.
Yeah, well, actually, how about this thing right here? Electricity likes to follow the shortest path, right? So where's the current going to flow? Right through the middle of me. And if I'm lucky, I won't die. Which is why it's actually not voltage that kills you. It's the ability of voltage to generate a current that kills you. 12 milliamps of current is not a lot of current, but it's enough to disrupt your heart and stop it from beating or start beating erratically. So this is a combination right now that we are doing of safety as well as units, because now we have this thing called a milli. What does milli stand for again?
1,000.
1/1000th. So 1 milliamp is equal to 1/1000th of an amp is equal to 1/10 times 1/10 times 1/10 of an amp. Each of these is 10 to the -1 power. Does everybody know their exponents? by definition, 1/10 is 10 to the minus 1 power. And you can add these together. So it's 10 to the minus 1 times 10 to the minus 1 times 10 to the minus 1, which is 10 to the minus 3 amps, which is also known as a milliamp. So 10 milliamps is enough to stop your heart from beating. So that is why when I'm in the field, if you have a circuit that's 480 volts, which is a very common industrial voltage, you have to get suited up to go anywhere near it. You have to wear gloves, you have to wear a face shield, you have to wear safety glasses, boots. In case there's a spark that forms, you have to wear an arc flash suit. So anyway. So now what we're going to do is a little bit of conversion on units. And what's important is to note that for units, all that we're doing is replacing powers of 10, as we just sort of did, but now I'm going to do a little more formally. So the question that I have for you is, if I have the number 10, how many times, to what power did I have to raise the base 10? 10 to the something is equal to 10.
1.
That's right, because 10 times 1 is equal to 10. That's it. It's just 10 times itself, or just 10 by itself. How about if I raise this to what power would I have to get to 100? 10 to the what power, which is 10 times 10 is 100. There are 2 of these. So 10, whoops, that was funny. 10 to the second power is 100. If I were to go with 1,000, equals 10 times 10 times 10. Everyone agree with that?
Sure.
Which is
Yes.
10 to the third power.
Yes.
Now, that has another unit. So let's say that I have 1,000, let's say dogs.
You
Well,
have a kilo
this
of
game-
dogs.
That's right. I have 1 kilo dog,
Oh,
because kilo
right.
is 10 to the third power, and I can just substitute the little letter K for that. So now, how about if I had 1 million dogs? Is 10 times 10 times 10 times 10 times 10 times 10 dogs. How many 10s do you see?
6.
6. And note that there are also 6 zeros over there.
Mega dog.
That's right. That is 1 mega dog. Right? It doesn't matter what the unit is. The key is just that we had 10 to the 6th power, and we could replace that with the big letter M. And the cool thing about this is that a lot of things do not have unit sizes of 1. That's just not convenient for a lot of things. For instance, if we were to say that we had, let's say that we had a capacitor, a 1 farad capacitor, which we're about to get to, is an enormous capacitor. That's an enormous ability to store charge. That's what a capacitor does. And yes, kilo is a small k. Okay, so 1 farad is a very, 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 very big capacitor. More than likely, what we're going to see is 0.22 nanofarads or 220 picofarads. Actually, let's replace that nano with a micro. I want to work with micro. So these are like very common. These are very common, very common prefixes that we end up using for capacitors. So here's micro. All right. So what does micro mean again? We go over to our chart. What does micro mean? 10 to the minus 6.
Hmm.
So now we can actually say this is 0.22 times 10 to the minus 6 farads. And there's a couple different ways to write 10 to the minus 6th. We can write this as 0.22 times 1/10 times 1/10 times 1/10 times 1/10 times 1/10 times 1/10. We can also write it as 0.22. We can multiply it out times 0.000001 farads. We can actually multiply it out if we want. That would be 0.0000022. Nope, 0.00022 farads. Okay, but I want everybody to notice, what do we now see here?
Lots of zeros.
Lots of zeros, right? Do the zeros really mean anything other than like a gross order of magnitude to us? What's really important is this number 22 or 2.2 or whatever it happens to be. So really the zeros just become a placeholder. And what becomes important is the fact that we don't have to carry them through because it's really a pain in the neck to deal with. So we typically will write it like this. The same reason that we write, for instance, 342,600,000.82 hertz. Right? That is a radio frequency. So the question is, does anybody actually want to see that? I sure as heck don't. I don't want that on my dial. I don't really care, especially because, you know, it doesn't really matter to go to all that detail. I mean, I guess it could, but for all intents and purposes, I don't really care. So what I would like to see is kilohertz or megahertz. So we can, the easiest way to do this is we start with our decimal point and we're going to slide it so that we get something that looks a little more neat. 1, 2, 3, 4, 5, 6 places, and now it's here. Okay. So what's our new number? 3.526000082. And how many decimal points did we move?
6.
6. So that becomes 10 to the minus 6 because we moved it to the left. But now, because we can't really make things disappear, we somehow have to take and replace those zeros that we moved away.
Is that minus 6?
No, sorry, that should be plus
Positive.
6. That should be plus 6.
You're seeing if we're awake.
There we go. Yes, there we go. So that would be
Makes me
plus
feel
6.
better.
Yes. So that would be plus 6, right? And it's still units of hertz. And now what do we do with that 10 to the 6th power?
Replace it with mega.
That's right. So now our new frequency is 3.526000082 megahertz. And, you know, to be honest, I don't really care what those digits are in most cases. So we just say, 3.526 megahertz. If I'm tuning my radio, I'd basically tune to that. And I don't really, for the most part, care about those extra little digits because they don't really matter all that much. But maybe I do. But the key is that I'm looking at megahertz rather than hertz. I could also convert this to kilohertz if I wanted to. And I would say 3.5260000.82. And I could slide this over now 1, 2, 3 places. That's 3.526 times 1,000 hertz. And that 1,000
Kilo.
that goes back over here to kilo or K. So that would be 3526 kilohertz. Or 3.526 if I carried all the decimal places, 0.0082 kilohertz. And that's how we move decimal places around.
You're killing
Hmm?
me. Being so sorry. kilohertz. You're killing me.
Okay, so now what we're going to do with these is, now that we understand decimal places a little bit, we're going to introduce something called a bell. And a bell is a way of comparing two numbers to each other. This was, you can probably guess who the bell is named after.
Alexander Graham Bell.
Alexander Graham Bell. That's right. But there's only one L in it. So the way that a bell is defined is a bell is equal to
Excuse me.
10 log base 10 of P2 over P1. Sorry, I'll get rid of the 10. There we go. Okay, so a logarithm is kind of like an opposite of an exponential. So if we said 10 to the 6th, that would be equal to 10 times 10 times 10 times 10 times 10 times 10. Right? Does anyone have any disagreement with that? Okay, so that would be 1,000,000. So now we can go backwards and we can say, how many times would you have to raise to the power, the number 10? How many times would you have to multiply 10 by itself to get that number?
6 times.
That would be 6 times. So the opposite of that is to say, what is the logarithm base 10 of 1,000,000? The logarithm is basically the number to which the base, which in this case is 10, would have to be raised equals that number. So basically what this means is that we had to raise this number to this power to get the result. And this is a way of dealing with big numbers in another way. The reason that we use this is because, let's take a look at this number. What is that number? That number is a trillion, right? Okay, so that would also be 10 to the 12th power. So how many bells would that be? And that would be the log base 10 of a trillion.
12.
Correct. Is equal to 12. Okay, so basically we would have to say, we would have to raise 10 to the 12th power to get a trillion. Well, what's nice about this is that this has now taken up all of those zeros with a base of 10. And what's also cool about this is that we don't need to carry all those zeros around. The other thing that's neat about it is that if we were to go, let's say minus 0.0000000000001 log base 10 of that, we could actually figure this out and say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Well, okay, that's actually 10 to the minus 12 power. So that would be minus 12 right there. So now we can take those two numbers, for instance, and say, okay, well, what we're going to do is now we're going to multiply this 1,000,000, or sorry, 1 trillion times 0.000000001. Anyone guess what that would be equal to? That would be equal to 1. That's right. Well, the easy way to do this is we now have this logarithm and this logarithm. And if we multiply these things, we just add their logarithms together. And the reason that's true is because 10 to the 3rd, for instance, times 10 to the 6th is equal to 10 to the 9th. If they have the same bases, you can just add the logarithm, you can just add the exponents together. Which means that if we have logarithms right here, that means we can just add them together. And the sum of minus 12 and plus 12 is 0. And by definition, 10 to the 0 is 1. So this is a really convenient shorthand way of dealing with really, really big and really, really small numbers. And where this really comes into play is when we start dealing with things like 0.00000000006, for instance. Things that don't end with a 1. Well, when we take a logarithm of that, we end up with something else. This might be minus 12.4. Well, if we have minus 12.4 and then we have a plus 11.6, we don't actually have to multiply anything together, do we? We just add them together and we get negative 0.8. So it becomes very easy to work with. Well, it also turns out that a bell is actually quite a large unit. So they decided sometime, I want to say in the 1930s, that the bell was too big and they created a decibel, which is a tenth of a bell. So the number of decibels of something is 10 times the log base 10 of P2 over P1. Now there's a unit of 10 thrown in there. So whereas we would get, like, let's say 3.6, now it's multiplied by 10 and it's 36 dB. So we're dealing with some numbers that are a little easier to deal with. You know, we don't have all those decimal places to worry about. So I don't memorize
In that equation,
what.
what were the P's in that?
Oh,
equation?
well, because it's a way of comparing one thing to another, those are power.
Okay, so could you say that a bell is it means a log number?
It is. Basically a bell is a logarithm of, it's a logarithm of a comparison of two different things. Like
It
how
doesn't-
much bigger is one thing than the other. And the easy way to write, what we're gonna do is we're going to now use decibels instead of bells. And we're going to use decibel is equal to 10 log base 10 of power 2 divided by power 1. So this basically just it gives you a way to represent what the change is between one thing and another. So let's say that we start at a power level, power 1 of 1 watt, and a power level 2 of 10 watts. Okay, so now we're going to plug these into our equation. 10 log base 10 of 10 divided by 1. 10 divided by 1 is 10. So this is 10 log base 10 of 10. So now we just have to look at that and say, okay, what is the definition of a log again? It's the power to which the base, which is 10, has to be raised to get the result. So 10 to the what power is 10? 10 to the first power. So this whole thing is 1. So we have 10 times 1 equals
10.
10. So basically, if we go up and we increase our power by a factor of 10, that is an increase of 10 decibels. That's one of the fundamental things to know. The other one is that, let's say that I double something. So my power to begin with is 1 watt, and my ending power is 2 watts. I just doubled it. So we're going to use the same equations, but now we're going to end up with something that looks a little bit different. We're going to have 10 log base 10 of 2 divided by 1 is 10 log base 10 of 2. And this is not a square number. This is actually not exact. 10 log base 10 of 2 is about 0.3. And you can go to your calculator and figure this out if you want. There's a whole bunch of decimal places after it. And you multiply that out by 10, and it's about equal to 3. So if you double your power, that is a change of approximately 3 decibels. And as they say, it's actually good enough for government work. It's good enough for engineering. Essentially, if it's close like that, that's close enough. So the only 2 things you need to remember, and these are honestly the only 2 things that I remember. 10 times is 10 dB. 2 times is 3 dB, and that's approximate. These are the only 2 things, no matter where you go in engineering, in radio, anywhere, you can get most answers that you're using, that you're looking for from those 2 things right there. Because I will go and I will prove that now to you. So let us say that we are changing from a power level to begin with, 25 watts, and an ending power of 100 watts. Okay. So tell me how to do this. How do we get from 25 to 100 just using doubling and tensing?
Double and double.
Double and double. Okay. So 100 is equal to 25 times 2 times 2. So our ratio is up by a factor of 4, and we doubled and doubled. Well, there's a times 2 and a times 2. Well, this translates to 3 dB, and doubling again translates to 3 dB, and we can add them together and we get 6 decibels. And it's really just that easy.
Well.
That's-
To you.
Well, no, but this is something that will be, if you use it, it will become very, very, very easy to look at. So let's go and go from 100 watts up to 800 watts. Okay, how do you get from 100 to 800 using factors of 10 and factors of 2? How would you get there?
Oh, you double the 1.
Yep. So the first
And
doubling
then-
gets you 200. So that's a
and
times
then-
2.
And then do that times 2 and times 2.
Yep. Okay. And every time you double, how many decibels is it?
3.
Yep. Okay. So what's our decibel change?
6.
dB.
12 D.
9. Right.
9.
Sorry, 9. Sorry,
That's it. That's the answer. That is a change of 9 decibels. And what's interesting and very useful about decibels is that when you start looking at antennas, you will find that the gain of an antenna, which is compared to, for instance, a reference antenna, which puts out a pattern that looks like this, your new antenna puts out a pattern that looks like this. The question is, how much more energy is sent out in the forward direction compared to with the original antenna? Well, what units do you think that might be measured in?
Decibels.
Decibels. So that is the same units, that's measured in the same units that you would measure power levels. So you can actually figure out, okay, if I use an antenna with, let's say, 7 dB of gain, and that means that I can conceivably have the same, let's say my transmitter is 1 watt. Actually, let's use 6, because 6 is easier to deal with. Okay, so I have 1 watt with a transmitter, with an antenna that has 6 dB of forward gain. Well, how do I break 6 dB into 10s and 3s? Everyone?
Double and double.
That's right. It's, whoops. 6 dB is equal to 3 dB plus 3 dB. And every time I use 3 dB, what does that do? 2 times? 2
Double.
times. Okay, and 2 times 2 is? So my actual 1 watt will look in the forward direction like 4 watts would look. And that's why decibels are so useful, because these are really easy to deal with. And because everybody deals with the same units, for instance, let's say that I now have a piece of cable connecting my 1 watt transmitter. Because everyone's going to have something called a feed line, which is a cable. And I have an antenna system that has, let's say, 10 decibels of gain. But I have cable, and at a given frequency, my loss is -4 decibels. Okay. What does -4 mean? Actually, you know what? Let's go -6. Let's make it worse. Now, you know what? Let's make it -4. So what does it mean if I have a gain of a negative gain?
Reduction in power, maybe?
That's right. That would be a loss. So now what can I do with these things? I can just add them together, can't I? So I'm
Yeah.
going to assume that I start at 0 decibels. And how much do I have when I get right here? I have -4
minus
dB.
4 dB.
And how about when I get up to the top?
6.
+6.
Yeah.
Okay. So what does 6 dB translate to? 3 dB plus 3
3
dB.
dB.
And every time I do a 3, that is 2 times.
Multiply by 2 times.
That's
yeah.
right. And that gives me 4. So if I have a 1 watt transmitter, my effective power going out would be 4 watts. If I have a transmitter that's 10 watts, what would my effective power going out be?
40.
40
40
watts.
watts. And that's how decibels are used.
Uh,
Now,
but,
this is actually really important when you start dealing with things like, okay, so we are working with dish antennas here in our club with a transmitter that is 400 milliwatts. We use it for long distance Wi-Fi over ham radio. We have a forward gain of 30 decibels because it's a pretty big dish antenna. So the question is, what is our effective power going forward? Okay, what is 30 dB? How would you break that up?
3 times 10.
10 plus 10 plus 10.
Oh, sorry.
Right? Okay, and every time you go up by 10 decibels, what does that translate to?
10 times the power.
10 times. So 10 times 10 times 10. What's 10 times 10 times 10?
1,000.
1,000. Okay, and we started with 400 milliwatts. And what does a milliwatt translate to? What does milli mean?
10 raised to minus 3.
Right, or 1/1000th.
Yeah.
So now we can multiply this 400 over 1,000 watts times 1,000 is equal to
100 watts.
400 watts. So from this teeny tiny Wi-Fi transmitter at 400 watts of power, because it's going through a very high gain dish, we have the equivalent of 400 watts of power pointing forward. That's a lot of power, isn't it?
Yeah.
And
yeah.
that's, now we have nothing going out in these directions. It's all going forward because of what we've done. So now let's take a look at something, and we're going to take this 400 milliwatt transmitter, and we're going to do something which we are legally able to do. We are actually legally able to, as hams, build our own antennas. We're actually allowed to build our own transmitters. So let us say that on this particular band, which we are allowed to do, we are allowed to transmit with a maximum legal output of 1,500 watts. Transmitter power. Okay. Now, what do we get from our 30 dB gain antenna? We get 1,000 times coming out forward, right? Which we already said. Everyone agrees with that. So what is 1,500 times 1,000?
1,500 kilowatts.
1,500,000.
Yep. We go 1, 2, 3, 4, 5, 6, 1.5 megawatts of effective forward power. So if anybody asks, why do you need to get a ham license? This is why. It's the same thing as you get, if you get a driver's license, they don't know if you're going to be driving a Ferrari or not, do they? You might be actually going out and getting a Ferrari. The driver's license is the same thing as would cover a tiny little car that has almost no power. Well, we don't know as a ham, because the license covers 1,500 watts with whatever antenna you want to use. We don't know if you're using a handheld radio at 100 milliwatts or a 1,500 watt amplifier, because the license is exactly the same, with an antenna that has 30 dB of gain with an effective forward power of 1.5 megawatts. So what would you use an antenna system and a power and an amplifier like this for?
Long range communications.
Yeah, what else? What else could you, what could you use it for? People actually do this. And I'm going to draw an application of this.
I'm gonna bounce off signals off the moon.
That's exactly right.
Hmm.
That's exactly right. And this is known as moon bounce, which as a technician class licensee, you are allowed to use those frequencies and those power levels and those antenna gains, or this is also known as Earth, Moon, Earth, or EME. If you have a big enough antenna, you can actually aim signals at Mars or Venus and bounce signals off of them as well, although it's a lot more difficult and takes a lot more time. Moon bounce is hard enough, but you're allowed to do that. And that's why you would be able to use power levels like that. And that's why it's important for us to understand decibels.
So there is no limit for the power at which the antenna can work. Like,
Well,
is there a limit?
There can be, yeah. Basically, your antenna has to be able to handle the amount of power that you're putting into it.
Radars and chips can burn incoming aircraft if we don't turn them off.
Yeah, you can do a lot of damage. What if somebody's standing in front of it?
Cook.
Yeah.
Yeah, I mean, you
So
can do a
that's
lot of
probably enough
damage.
to, like, cook a bird or something, right?
Yeah. Oh yeah, absolutely. So,
So in
okay.
this case, I'm only really familiar with decibels being a sound unit, but in this case, it's totally different. You're saying
No,
that
it's
this
actually
is,
exactly the same.
or is there a physical sound that your ears can register coming off of this thing?
Well, the key is that a decibel has to be based on something. There's some ground level, base level, and 0 decibels is the threshold of audibility. So there's your starting point. So because without that, you can't calculate anything. So basically 0 decibels is when you can, that sound level that your ears can no longer, that an average ear can no longer hear anything. And it's also measured at distances, because a jet engine at 10 feet is a lot different than a jet engine at 1.5 miles. The sound pressure is very different. So
3 decibels will be twice as loud.
it depends on, it depends sometimes, like on voltage, you can have voltage decibels, and because power is equal to the square of voltage, it's 6 decibels is twice as big in voltage, but we don't usually work with that. In power, like sound, and in wattage, wattages of radio signals, for instance, we do deal with 10 times being 10 times as loud, 3 times, or 3 decibels being twice as loud. More often than not, we just deal with power, and sound is power as well.
Does this apply when the examples you gave, 2x 3 dB and 10 is 10 dB. Does that work in the inverse? One
does.
half is -3
Exactly.
and 1/10 would be -10.
That's exactly right.
Thank you.
So that is the basis. And to be totally honest, I've been doing this since I was 17 years, actually since I was 15 years old, and all through engineering school. Yeah, you have to calculate exactly, but you know, as far as this goes, I've been doing this since I was 15 years old. And those are the things that you can get a rough order of magnitude on. You know, if you just know those things, you know enough to get an idea. If you want exact numbers, yeah, then you know you'll go through the calculations, but then you're doing a calculator anyway. But just for a rough order of magnitude, 10 dB is 10 times, 3 dB is twice. And in fact, that shows up on later exams and as well when you're looking at filter cutoffs and things like that. Those are labeled by half power points. And a half power point, how many dB would half power be? It's known as the 3 dB point.
3 dB. Yeah.
It's known as the 3 dB point. So
You're only as good as your metering.
yeah. All right, you guys ready for a 5-minute break?
Sure.
Okay. And next up is circuit design.
Please mute before you take off.
Any questions before we go on? Now's a good time to ask.
Doesn't a lot of this kind of end up being sort of much ado about nothing when you're so dependent on atmospheric conditions and things like that?
Well, I mean, yes and no. It depends what you're doing. I mean, if you're putting in an antenna system and you're putting together a radio system with a piece of cable with an antenna on the roof of your car, yeah, it totally matters.
But like what would matter would be more like relative change as opposed to like actually trying to calculate, say, how far you should be able to throw given a certain amount of dB and distance when everything else is kind of in flux. I mean,
okay,
like,
here's the practical application. So let's say I've got a 5-watt handheld that I use as the radio in my car. And I use that and I use a piece of cable that induces, let's say, 10 dB of loss, and I have an antenna that has 3 dB, or let's say 4 dB of gain, which basically means I have 10 dB of loss and then 4 dB of gain, which gives me a net of -6, which means that I now know that I have a 5-watt transmitter and a quarter of it makes it out, right, in all directions, which means that I now have a 1.25 watts going out of my antenna. If I just upgraded my cable to something that had less loss, I would essentially have more power going out. If I got a better antenna, I would have more power going out. So I mean, it really, the real practical application is system design. And then you also look at what your expected path loss is between 2 points. If you're doing, if you're going through, ionospheric stuff, right? You can't really predict that. But if you're looking at point-to-point communications, let's say 10 miles apart, and you know that it's an unobscured path and it's not raining, even if it is raining, but if it's that it's typically not raining, you're going to have, just by the fact that your signal is going to be spreading, you're going to have some loss in your signal by the time it gets there, but you can predict that. But then let's say that that you want to be going out to 20 miles, the signal gets weaker, and then there's a hill in the way. And that's really where it comes down to it. I mean, when they say, remember the TV commercials when they were testing out the cell phone system, they said, "Can you hear me now? Good. Can you hear me now? Good." That's what they were doing. They were basically making a coverage map based on path loss, because that one of the things that you do is you look at what your expected path loss is if you have a fixed location. If not, if your location is going to be changing, then you really will find that a bigger, it might be a higher power transmitter, it might be better cable, it might be a bigger, higher gain antenna that does the job for you. But on top of that, remember that a bigger transmitter doesn't make your receiver any better, right? What does make your receiver better is not wasting the signal that's coming in through the antenna down to the receiver. That antenna gain and loss and cable gain and loss, or cable loss, work on transmit and receive. So that's why there's a rule of thumb which basically says the first thing you want to do to improve your station's effectiveness is improve the antenna and feed line. The last thing you would ever do, because it requires all kinds of other stuff too, is get an amplifier. That's the last thing you would do.
I had another question. Is the Wi-Fi thing you were talking about, is that part of the HamNet project?
Yes. Actually, the whole HamWAN thing. Yeah, it's repurposed ubiquity routers. And with a standard ubiquity router with a high gain antenna, you can get coverage up to about 30 miles.
That's like super directional though, right?
Yep, exactly. It's super directional. So basically it allows you to connect from point to point, like mountaintop to mountaintop.
I used to play a game called Ingress, and people would use the like the little Ubiquiti 900s. They would set up if a location was obscured like obscured ability to use a satellite terminal, they would set up a terminal that had line of sight to not Hughes. I don't remember who's the big satellite internet providers.
It's Hughes.
Well, that's for like in place. I'm talking about like mobile.
Okay.
They would choose a place that had line of sight for that, and then they would set up like 2 900 megahertz like point-to-point Wi-Fi routers and shoot Wi-Fi into the location that they needed. It was really interesting stuff.
So there's something that's going on right now called ARDEN, which is Amateur Radio Emergency Data Network, which is basically doing that exact same thing, except that it's a self-healing network, and you basically will set up point-to-point links, but then beyond that, you can have access points that people can tie into either over the internet or using radio as well. And so one of the new things that's going on right now is actually taking, because it's all internet based, it's all IP, is repurposing old PBXs, telephone systems, to operate over ham radio. You're muted, Greg. You're muted.
No, that's cool. So my friend who told me about this class actually did this same class maybe last year, and he's the one who told me about all this.
Yeah, and actually, one of the guys here he was an administrator who was dealing in telephony, like actual PBX networks, and he had an old PBX, so he has, a radio telephone on his desk, and two people in different places can just pick up the phone and dial each other over the radio. And what's cool is that it's actually full duplex.
What's the latency on that?
Well, it's not bad if you think about it. I mean, there is supposedly 30 miles is a practical length on the link because of the latency, because you're basically, you're looking at the speed of light, and it's 1 nanosecond per foot. And at the data rates they're talking about, it's not bad, but that's what gives them the practical, a practical path length that they can get away with. So,
thank you.
Yeah. Any other questions before we go?
Why is the current, which is measured in amps, called I?
For impulse.
Oh.
It was because it's a French thing, ampere. Yeah. Well, impulse. Okay. So we're now on to electronic components and circuit diagrams. We're on page 15, but we've actually already covered a lot of this stuff. So what we're going to do right now is we're going to share this whiteboard, and we're going to draw this, which is a resistor, and this, which is a capacitor, and this, which is an inductor. And then we're going to add another thing called a diode. Okay, so this is a resistor, capacitor, inductor, and this is a letter R, this is a letter C, an inductor, again, multilingual, this is a letter L, and a diode, we're going to put a plus and a minus on it. Now, if you look at the resistor and the capacitor and the inductor, the resistor is basically just a block of a material that doesn't let current flow through it so easily. A capacitor is much more interesting. So what we're going to do is we're going to, we'll first take this resistor and we'll do this with it. That makes something called a potentiometer or a pot. And it's a variable resistor. So this could be a pot that would now be like 0 to 50K. There can be a knob on it that basically allows you to change the value. And that would be measured in ohms. That would be called a pot or a potentiometer. And
what is that word?
A pot.
Oh, potential, for potential?
Yeah, potentiometer.
Okay.
Also known as a pot. So that'd be like a 50K pot. Now, these can actually be tapered so that they're linear, so that if you move it 10%, you get 10% resistance. They can also be an audio taper because audio deals with voltage squared. P is equal to I squared R is equal to V squared over R. So depending on whether you're doing voltage or audio, you would pick a different taper. So when you go to look at that, it's not something that you'll have to know for this test. You may never need to know it, but basically what it means is that when you go to pick one, you'll actually see that there's a voltage taper, a linear taper, and then there's an audio taper as well.
But I was just wondering, what's the difference between a trimmer and a pod? Like
they're the same thing.
Okay.
A trimmer is usually just something that is very, very small, and very often a trimmer is a capacitor.
Oh, okay.
Like a trimmer cap.
Mm-hmm.
Okay, a capacitor is literally drawn exactly as it is. It is two metal plates separated by some non-conducting material. It could be air, it could be plastic, it could be paper, it could be pretty much anything. But essentially, it's two conductive plates connected by some non-conducting material. So now we're going to take this capacitor and we're going to hook it up to a battery. Okay, so let's hear it, everybody. What do you think would happen when we do this? If the voltage is not so high that the capacitor blows up?
It will.
Well, we'll get all the pluses that flow out of the battery and they'll end up over there. And what'll happen on the other side?
Nothing.
We'll just get minuses.
Yeah.
All the minuses will flow to that side. And then what happens when it's all filled up? There's no more space. Yeah, it's completely charged. So if you think about it now, what happens inside right here where every plus and minus are lined up? What do you know about opposites?
And to attract.
They attract.
So you
So what's
create
happening
drift.
is that these plates are trying to squeeze that central material so they can squish themselves together. They generate something called an electric field. Because these are electric devices. They are pluses and minuses. They generate an electric field, which is trying to pull the two things together. Well, the material in the center is fighting back. And that basically creates a storage of energy. In other words, the fact that these are charged means that they are, storing energy. And the dielectric in the center, as it's called, is basically resisting that force, which is trying to pull them together. So it's essentially creating a fully charged thing that's now storing energy. So a capacitor stores energy in its electric field. Now, interesting about a capacitor, what would happen if I took the battery off? What would happen to the charge?
It'll stay there.
It's just going to stay there. It has nowhere to go. Now, what would happen if I do this?
What did you do?
I just connected the two lines. What would happen if I just took that capacitor and I shorted it out?
You create a flow.
It'd create a flow. And then the pluses and the minuses would all balance out. And then you would now have an uncharged capacitor. So that's really actually pretty important because that means that a capacitor can also be used as an energy storage device, kind of like a battery. Like basically I've put charges on the two plates and I've used it to store energy. Capacitors, if they're really, really high values, are actually called ultracapacitors. And they can actually be used as a temporary battery storage in a way. That's a very, very high value capacitor. The ability of a capacitor to store energy is known as its capacitance. That's the ability of a capacitor to store charge and energy. That's its capacitance. Or you can think of it as its capacity. And this is actually measured in farads, named after Michael Faraday. So now we're going to actually show you something interesting about a capacitor. If we take this capacitor and I hook this up to AC, what do we know if I draw AC? AC looks like what shape? Ideally.
Sine waves.
A sine
Sine
wave.
wave.
Okay. So a sine wave goes plus and minus and plus and minus and plus and minus. So I'm going to hook this up right here. Okay. So now I'm going to draw the plus and the minus. So what will happen when the plus comes up is that I get pluses over here and I get minuses over here. All right. Now, if this were being hooked up to a plain old battery, it would just charge up and stay there forever. But what happens is now we're into this section down here. During this time, the plus and the minus on the battery swap. They change positions. And now my plus is over here and my minus is over here. Well, all these minuses, they're being attracted over to the other side, but they're being more attracted. It's an easier way to get back to where they started, isn't it? So now they disappear from here and the pluses disappear from over here. And then eventually we end up with pluses over on this side and minuses over here. Does everyone agree with that?
Yep.
Okay, except then we get back to this point right here. Well, what does that mean? We got to switch the battery again. That's our new plus and our new minus. And all these things get attracted back to where they came from. And then they form over here. We get our pluses over here again. And our minuses on the other side. So what does this really mean? If I just did this forever,
On, off, on, off.
on, off, on, off. The capacitor, okay, what does the battery see? If I were in the battery, what would I see? I would see current flowing this way, and then this way, and then this way, and this way, right? Let's say I didn't know what was on the other side of the wall. So here's the wall. Let's say that I'm in the battery and I didn't know what was on the other side of the wall. That this is all a big mystery over here on the other side. What would I assume would be on the other side of that wall? If I'm seeing, when my voltage switches, if I'm seeing current flow back and forth and back and forth, what's that the same as?
Having a short.
Each other out.
Having a short. That's exactly right. In other words,
You know what?
having a short circuit.
Oh,
If I don't know what's on the other side and I am in the battery and I just see my voltage causing current to flow back and forth, well, the simplest thing that I could assume is that there's just a short circuit on the other side because I don't really know what's over there. As far as I'm concerned, there's just a short circuit. So this is really important because when a capacitor encounters a DC voltage, it charges up and then doesn't take anymore because there's no more room. When a capacitor encounters an AC voltage, this capacitor that's here acts like it's not even there. It just becomes a short circuit. It allows the voltage to flow back and forth. It allows the current to flow back and forth. So what this really means is that if I were to hook up a capacitor across an AC circuit, the AC flows right through the capacitor and the DC does not. So let's say that I had some weird voltage source that looked like this, AC and DC. So if I were to put this on a graph, it would look like this. Okay, so this is AC, right? It's bouncing up and down, back and forth, but does it ever change direction? It's always above zero, isn't it? It's just a different amount above zero. But you could actually draw this as instead of that, I could actually draw it as the sum of this and this. Right? If I were to add those two things together, the result would be something that looked like this. It would always be above 0, but it would be bouncing up and down. Well, here's what's kind of crazy about this. If this is my voltage source, and I put this through a circuit that has a capacitor here and a resistor here, my current would get to this point and it would have to decide which way to go. What do you think would happen?
The AC current will go through the capacitor.
The AC goes this way.
Yeah.
And the DC goes this way.
Yeah.
It actually would split them apart. Because the AC circuit, because the capacitor looks like a short circuit for AC, and because electricity likes to follow the easiest route, the path of least resistance, there's basically very little resistance for the AC going this way. And the DC voltage would basically charge up the capacitor and go nowhere. So obviously it's not going to go that way. So the voltages that you see right here would actually be split apart. This is actually really important, and we're going to get to exactly why in just a minute. So now we're going to add something called an inductor. And what I want everybody to do is hold up your right hand, not your left hand. If you do your left hand, it won't work. Okay. Take your thumb and wiggle it, just so I can see everyone wiggle their thumb. Now take your fingers and go like this and roll them forward. Okay. So basically, if you have a current going in the direction of your thumb, it generates a magnetic field that loops around the current in the direction that your fingers go forward, which basically means if I have current that's flowing this way on this page, I can hold up my hand and say that my current is going into the page, making a loop and coming out of the page down here and coming back up to here. So basically it's making a loop. My magnetic field would be making a loop that goes into the page here and out of the page over here. And I could draw more of these. Into and out of. The into is an X, meaning it's disappearing into the page. And the out of is a dot, meaning it's coming out of the page. So basically I'd have all these loops indicating what my magnetic field would look like. So the same way that a capacitor has energy that's stored in an electric field, a wire carrying a current generates something called a magnetic field. Now, I want to bring something up. What are the two parts of an electromagnetic wave?
Electric field and magnetic field.
Yeah, okay. So we're getting to some kind of convergence here, aren't we? Because we're talking about electric fields and magnetic fields and how these devices make these things. All right. So now what I can do is I can take this wire and I can actually coil it up like this. Well, if I take this magnetic field, which had existed in loops around the wire, essentially this thing that I've just drawn is called a solenoid, which is basically a coil of wire. And if I have current going through it, and that current is required to go around the loops, essentially what I will get is a magnetic field that now goes like this as it changes direction. And it will look like basically a hot dog going around it. You'll have these magnetic field lines that form like this. Strongest toward the center, it goes right through the middle, and then they return back to the outside around the outside. And this thing will generate poles, north and south, if everyone's ever seen a magnet. You'll basically have a north and a south pole. The poles themselves are not particularly important for this case. What is important, however, is the fact that you have this magnetic field. Okay, so if you have current going through a piece of wire, we know that a wire is a pretty good conductor, right? It has very low resistance. Ideally, what you want to do is you want to have a superconducting wire, which has no resistance at all. That's why people are working on superconducting wires for superconducting magnets. But for all intents and purposes, we're going to assume that this is a perfect wire. Well, okay. So now what happens if you have a current flowing constantly through this wire? You'll have a constantly existing magnetic field. Everything's great, right? You got power, you have energy that's stored in this magnetic field. Everybody's happy. The current flow, DC, is great. It goes right through it like it's not even there. It generates this magnetic field. But then what happens when you switch the direction? And this magnetic field with a north and a south pole has all this energy stored in it. What would happen if you tried to switch it around? Where does all the energy go?
Hoses.
Where does it go?
It may have to dissipate as heat.
You have to get rid of it somehow.
Yeah.
Right? So, well, okay. Well, how are you going to do that? I mean, let's look at this in the worst possible case. So we have a magnetic field that exists, and we have a lot of energy stored in it. So I'm going to draw this coil again. And I'm going to hook it up to a battery with a plus and a minus. All right, so we have our current flowing this way, and we have a magnetic field that basically looks like this. We have magnetic field lines going out into space, and you have all that energy being stored in a magnetic field. Well, okay, now I'm going to do a horrible thing. I'm going to disconnect this battery completely. Okay. Capacitor stores energy in an electric field. An inductor stores energy in a magnetic field. Where does the energy go?
Out through the circuit?
Well, it has to, but there is no circuit. I just disconnected it, didn't I? So I just disconnected the circuit completely.
But it's storing energy.
Well, that's right. There's energy there somewhere, but where does it go? It can't just be stored in space. Yeah, it has to go somewhere. Well, okay, if I left these two terminals here, what'll happen is that you've got all this stored energy that's stored up in this magnetic field and nowhere to go. Well, energy can neither be created nor destroyed, which means you can't store it. It's got to go somewhere. So this is the easiest place for it to go, isn't it? Except this is a big open space. So what will happen is, has anybody ever worked on their car?
Worked on their car?
Yeah.
Yeah, kind of.
Yeah, okay. Has anybody ever seen an ignition system on a car?
No.
Ever heard of a
Ignition
coil?
coil.
Ever heard of ignition coil?
Yeah.
Yep.
Does anyone have a car that's old enough that it had points?
Yep.
Okay, these are points. Basically, what you end up with is a gap that you then open up between.
Well, you're going to get a spark.
And you're going to basically have all that energy, and what it's going to do is say, okay, I've got all this energy stored up. I've got to go somewhere. Zap. So it builds up voltage that goes higher and higher and higher until it figures out how to get rid of that energy. And if there's a resistor across it, like a very high resistance resistor that you've conveniently put there, it'll go through there. Very often what we do is we add something right here.
Oh yeah, that's flyback diode.
That would be known as a flyback diode. That is designed to dissipate the energy that's stored in the magnetic field. If
A
this is
flyback what?
a flyback diode or a snubber, which is designed to protect the electronics, to keep them from being destroyed by that suddenly high voltage that exists.
Is
But
it a
if
reflector?
Hmm?
Is it a reflector?
No.
Does it reflect things back?
Nope.
No.
So we're going to get to diodes in just a second. That's the next thing we're going to cover. Basically, what you end up with is that power has to go somewhere, the energy has to go somewhere, and it generates a very, very high voltage and generates a spark. If this is in your car, you take these lines and you run them down to your spark plug at the right time, and it ignites the fuel in your engine and makes your car run. So
Is that how you get a radio spark for transmission?
That is how a spark gap transmitter used to be made a long time ago. Now, the thing is that a spark generates radio frequency energy on a lot of different frequencies. It's very broadbanded. So what you would do is you would put this through a filter, and you would try to generate just the frequency that you intended to do. Spark gap transmitters these days are illegal because they are horribly noisy. Those went away a long time ago, but yes, that's how people built something called a spark gap transmitter a long time ago. They sounded like it was
awful.
awful.
Morse code, doesn't it?
Yeah, well, I mean, you could use it for Morse code, but yeah, they were terribly noisy, and they made an awful sound. Okay, so what we're going to get to now is a practical use of these things. Actually, they on the bottom of 16, they're making us just mention a couple other things, so I might as well. We're talking about batteries a little bit. So some batteries are rechargeable, some are not. A battery is basically just a way of storing energy in a chemical reaction. A rechargeable battery is a reversible chemical reaction. Your car battery, for instance, lead acid, that's a rechargeable battery, thankfully. That's a reversible chemical reaction. When you put voltage into it, it reverses it backwards. Nickel metal hydride, lithium ion, lead acid, NiCad, those are all rechargeable. A non-rechargeable battery, for instance, would be like a carbon zinc battery. That's your old standard heavy duty battery, your AA cell that was labeled heavy duty, which really wasn't heavy duty. Alkalins are way better. Alkalins are also, unless they're rechargeable alkalins, they're not rechargeable. Your lithium button cells that you use for 10 years in your smoke detector or your watch or clock, those are not rechargeable either. A device used to connect or disconnect electrical circuits would be known as a switch. We're about to get to that. And an electrical component used to protect components from current overload, that would be a fuse or a circuit breaker. All right, so now we're on to semiconductors. We're on page 17. So what I drew, when I'm going to draw that again, I'm going to draw that inductor with its magnetic field around it. Okay, so now what would happen if I were to take a battery and hook this up? So which way would, if I had my current going this way, my current gets here and it splits, which way would my current prefer to go? Likes to go the path of least resistance. Could very well be pretty equally split, right? Well, I don't really want to be doing that. I mean, why would I want to be heating up this resistor when I really want to just run this inductor? So what I would need is a traffic cop that would say, you're not going that way. That is known as a diode. A diode is a one-way device, which is made of silicon. It's known as a semiconductor. And it has P material and N material. Actually, I drew that backwards. P material and N material. like that. All right, and this is the cathode. The cathode on a diode is marked with a stripe. It looks like that. This is the positive terminal. This is the negative terminal. The important thing about a diode is that it only runs in one direction. It goes from plus to minus. So if I go through this circuit, what I will find is I'm plus here, plus here, plus here. But what do I get to on the diode? I get to a minus. That means that the diode is backwards, which means it's not going to work. Well, that's actually really good in this case because I didn't want it to work. Now, when I disconnect this and take the power supply away, all of a sudden I have this being gone, and this being gone, and this being gone. And all of a sudden I'll have a voltage here being generated by that magnetic field, and the current will flow this way through the resistor and back over to here. And since the plus gets to the plus terminal of the diode, which is a one-way device, at that time, it allows the current to flow and it dissipates the energy in the resistor. And in this case, this is known as a flyback diode. And it's used to protect your electronic circuits. Okay, so a diode, again, has two terminals, anode and a cathode. This is plus and minus. If you look at it physically, there's a stripe on the cathode end of the diode, indicating the negative terminal. Notice it even kind of looks like a sideways minus sign. The important thing about a diode is that a diode will only conduct current in that direction. If you try to run it backwards like this, unless it's a very special kind of diode, it doesn't allow it to flow. So it's a one-way device, which is really profound. Internally, this is actually made of two different materials. They're both silicon, but this has a few extra pluses in it, and this has a few extra minuses in it. And because of that, this is known as P, and this is known as N. There are different kinds of silicon, which are then P and N.
It's the arrow. He's using conventional flow.
Okay. An LED is a special kind of diode called a light emitting diode. It flows in the positive direction, and when it does that, it emits light. They can be in all different colors. We see them all over the place now. Okay, so now we can take a couple of diodes and put them back to back and build something really cool out of it. We can make a P and an N, P. We can make a sandwich out of those out of those different things. And in other words, we can basically say we have a PN diode here and a PN diode here. And now we have three terminals, and this would be known as a PNP. Typically, we draw it like this, P, N, P. And this is something known as a transistor. And this is something, if we start labeling our three terminals, this is our collector, this is our base, and this is our emitter. This is known as a bipolar junction transistor, or a BJT. And what's nice about this is that we end up with current that can flow from P to N like this. When that happens, we open up a channel that goes this way that can handle much more current. So what we end up with then is something called gain. We could measure that in decibels if we wanted to. This is the ability of our device to make a much bigger copy of a signal that exists between the base and the emitter. And what's cool about that is now we have essentially two isolated things where we can take a small signal, usually in the form of a sine wave, and make a really big signal over here. That's an exact copy of it. And this is known as amplification. Right? So we can use our transistor as the central device in something called an amplifier. We can also use it as a switch. If we just turn it on and we run this to the point where the big is like really big, we just slam it on as high as it can go, this becomes a switch. This is the basis of what is going on inside every computer and every cell phone that you have. Basically, transistors used as switches to store values of ones and zeros. Okay, the class of electronic components that use a voltage or current signal to control current flow is known as a transistor. They can be used as an electronic switch or an amplifier. The ability of something to make a bigger copy of a signal is called gain. And inside every amplifier, you will find, unless it's a vacuum tube, you'll find a transistor. Okay, three layers of semiconductor material. So I can draw it like this. This is the common way to draw a transistor. And it's going to have an arrow, kind of like the diode did. This is known as an NPN, because if I were to draw the semiconductor material, it would be NPN. Because we have PN, the current flow would be this way. And then we'd get a really big current flow this way. The easy way to remember this is the fact that it's not pointing in. Notice your arrow is pointing out. So an NPN, not pointing in. A PNP would be pointing the other way. And it would, all the currents would be backwards. Okay, so there's another kind of transistor called a FET, which is a field effect transistor. If I were to draw this, you might recognize something that's in the center of it. Somebody blurt out what that looks like right in the middle.
Capacitor.
It looks like a capacitor. What does a capacitor do? When you put
charge.
It collects charge. If you put a plus here, what's going to form on the other side? You're going to get minuses on the other side.
Yeah.
So basically, by changing the voltage,
Hammett.
What? So by changing the voltage that exists on one side of that plate of the capacitor, you're going to change the voltages that exist on the other side. So a small change on the left-hand side will change the right-hand side a lot. That is known as a field effect transistor. They're a lot more efficient than the bipolar junction transistors because there's no actual connection between the inlet and the outlet. Okay, so now we are on page. We are on page 19, and I will hopefully share this. Okay, everybody see it?
Yep.
Okay, so item number one, what would item number one be? Everybody. That's a resistor. How about number two?
Resistor.
Transistor. Okay, so looking at the arrow, would that be PNP or NPN?
NPN.
NPN, because it's not pointing in. Exactly right. Okay, item number three would be like a light bulb. And what is item number four? The plus and minuses aren't drawn, but yes, that's a battery. Okay, so how about item number five there?
Ground.
That's a ground. Okay, so we haven't talked about ground yet. And the easiest way to talk about ground is to say that ground is 0 volts. So ground is our 0 volt reference, basically saying that it's the voltage of the surface of the earth. That's literally what ground means. So if I were to draw that, I would say that this is 0 volts. All right, so that's our 0 volt reference. And notice that it exists there and there and there at all 3 of those points. Well, how do I know that those are actually all the same point?
Same symbol.
That's the same symbol, and they're all connected to the earth. And it's assumed that the earth is a perfectly conductive thing. So our 0 volts is connected everywhere. So really, if I wanted to, I could actually make it so that I would actually draw it like this.
Like what? I'm not, oh,
And I could get rid of the ground symbols. I could connect all my grounds to one point if I really wanted to draw it that way, because they're really all the same. Okay, so now that I'm going to erase that, the way we look at this circuit is that, okay, we basically have this half of the circuit. And then we also have the upper half of the circuit. Okay, so when this goes positive and this is negative, what happens through this diode? Remember, a diode, if it's pointed in the same direction as the voltage, it's going to turn on. So what happens is if the voltage is positive coming in, current device number 1 is a resistor, so it limits the amount of current that flows. It turns the transistor on. And then once the transistor is on, this channel from top to bottom becomes open. Well, this is plus again.
Light comes on.
And this is minus. And we go like this. And our current flows that way. Our current flows through the light bulb, which turns our light bulb on. And this is an example of an electronic switch, which is exactly like if I take my iPad or my iPhone and I do this and I turn it on, there's an electronic switch that turns on the LED. So that's a remote electronic switch. Okay, that can also be used for something like a remote lighting circuit on a power pole, or 100-foot tall lighting, 100-foot tall lighting stanchion at a baseball stadium, where nobody really wants to climb it to throw the big switch. Because why would you want to do that? Okay, so here's another one. What were the sideways Ys?
The question, Scott.
Okay, Jim, you got to explain what were the sideways Ys?
what were what?
They were the figure on the very far left of the last circuit.
Sideways Y. Oh, that's just basically a terminal plug where you plug something in. Yeah, you just plug a terminal, like a connection into it. It's literally like a receptacle.
Can you go back to that?
Mm-hmm.
Okay, the little Ys that look like lying down people, that's the terminal plug-in?
That's like a socket. Yeah, and
Okay.
basically a plug would plug into the socket.
Okay.
And what
Okay.
is 4?
4? 4 is a battery.
Oh, okay.
So this is a little battery operated light bulb. Basically, this is the light on your cell phone.
Okay.
Okay, so now this is going to be a little more complicated, but very, very cool. Okay, so we are now going to introduce something called a transformer. All right, so let's look at, as I bring up the annotation on this, and I do this. Okay, what is this thing that I just circled?
Primary flow.
Right, but what is it? I mean, if you were to just take it by itself, what is it? We just talked about it a minute ago.
Inductor.
An inductor, okay. And what is this one over here?
Inductor.
It's another inductor, okay. So, but notice what's different about them is that we now have them going around what looks like a common something or other. Well, what this basically is, if we were to draw it, is that we would have a big rectangular blob, which is actually a solid mass of iron or steel. And we would take our first coil, our inductor, and wrap it around that side, and our second coil and wrap it around that side. Well, if you remember what we drew, every time we draw a coil and put a current through it, we get a magnetic field. Well, magnetic fields, you may remember, like if you made an electromagnet, you wrapped a piece of wire around a nail and you could use it to pick up paper clips. The reason that you did that was because that material, steel or iron, is a ferromagnetic material, and it tends to constrain magnetic fields really well. So what ends up happening is you end up with a magnetic circuit now that flows around on the inside of this core. You get most of your magnetic energy that is now stored on the inside of the core. Well, if a current makes a magnetic field would make a current on the other side. And what it turns out is that the number of turns of the coil around that core is proportional to, if you take the two of them, N1 and N2, that changes the overall voltage and current on the opposite side. So basically, if I have 120 volts AC, because it only works at AC, and this is a 10-to-1 turns ratio, this is the way a transformer works, I will have 12 volts AC on that side if I have a 10-to-1 turns ratio. And this is actually really important because what do we know about energy?
Can't be destroyed.
Neither created nor destroyed. So that means that if I have a different voltage over here, what does that mean about my current? Because my power has to be basically the same. My power is the same, which basically means that my current is going to be, let's say, 1 amp on this side, and I'll be able to make 10 amps on this side because power is equal to volts times amps. So what it allows me to do is change my voltage and change my current. Okay, so this can be used to increase voltages, but it only works for AC again. This can be used to increase voltages. It can also be used to decrease voltages. If it's going up, that would be a step up transformer. If it's going down, that would be a step down transformer. In this particular case, the assumption is that I have, let's say, 12 volts AC on this side. Okay. Now we're going to start to get into some really cool stuff, because if I were to draw this, it would look like this. Right? Here's my sine wave. And it would go plus and minus. Well, what is this device number 5 up here, everybody?
Diode.
A diode that has a plus side and a minus side. If I get a plus over here, that means the diode is happy and I get current flow through it. But if I get a minus over here, that means that the diode is not going to turn on, which basically means what will happen is when I get a plus, I get a voltage that goes through. I get current that passes through. When it goes minus, I don't, which basically means that what I'll end up with is something that looks like this when it gets through the diode. Okay, so now
what does the straight line represent in the
that's
loop?
our 0. Because originally this was a sine wave, right? This actually used to go like this, right?
So it's still proceeding, but it's,
It's chopped in half.
and then
Because
how does it pick up again?
well, because it's still there. The voltage is still going up and down, but but the diode doesn't allow the minus parts to go through because the diode is turned backwards. So what that does is effectively take these minus parts and make them disappear. And when they disappear, what does that look like? Does the voltage ever go negative?
No.
It doesn't. If the voltage never goes negative, what's this known as? That is known as DC. Now, it's really ugly, right? You would like your DC voltage to be pretty stable so you can run something off of it, but this is actually DC. Okay, well now we have this device number 6. Okay, now we get to device number 6. And what do we see about device number 6? What is that?
Capacitor.
A capacitor. And what happens when the voltage goes high going into the capacitor? It charges up. But what happens when the voltage drops down to 0? What does the capacitor do? It starts to discharge, but it recovers. It recovers the 0 volts and starts to dump its energy onto the circuit. So that right there becomes a little bit filtered. Essentially, the capacitor sort of acts like a battery. Okay, well now, if we have a lot of this, and it's a really big capacitor, maybe we get a nice smoother thing that looks like this, which is still a little bit bumpy, but not bad. Okay. Number 8, what is number 8?
LED.
That is a special kind of diode that has lights, that has arrows coming out of it. That's called an LED, a light emitting diode, just like this. All right, so now basically that functions as an on-off light. Essentially, if we have voltage here, it makes current flow down through here, turns the LED on, indicating that the power supply thing is turned on. What is number 9? I could actually draw this resistor like that. Special kind of resistor.
Potentiometer.
That's a potentiometer, which allows me to change the resistance. This allows me to be a current limit as well as a voltage limit. Really, it's for current limiting. And remember I said that every diode conducts only in the forward direction? Well, for every rule, there's something that goes against it. This is actually called a Zener diode. A Zener diode is a backwards diode that has a voltage reference. And what this basically does is say that I am picking my diode to say that I'm going to operate at 9 volts, and anything above 9 volts, I'm just going to allow to go down into the trash. I'm just going to basically cap the voltage at 9 volts.
Does that make it a voltage regulator?
That makes it a voltage regulator. And what comes out of that is a nice, smooth DC voltage. And what do we use nice, smooth DC voltages for?
Electronics.
Electronics, because electronics hate voltages that go up and down. So if I were to take this and I were to rip this power supply apart, I would find that this had a couple of diodes in it, probably an integrated circuit, and it would basically work in that fashion. It probably has some really big capacitors in it to smooth things out. Okay, next. Okay,
You drew an arrow through your number 9 resistor to show that it is,
a potentiometer.
okay.
The way that they drew it, it's also a potentiometer. So that's why I did it that way. There's 2 different ways to draw the potentiometer. Okay, finally, we're going to be getting to this thing. This is actually a really important circuit, which gets kind of short shrift here. But it's a very simple looking circuit. All right, so what does everybody see in this circuit?
Variable capacitor,
two variable capacitors, and
variable inductor.
a variable inductor. Number 4 is an antenna. Okay, now, what did we say about inductors and capacitors and stuff like that?
They store energy in electric and magnetic fields.
They store energy in fields, that's right. And what's cool about it is that we basically end up with a system where they store energy in inductive and magnetic fields. Okay, so there's nothing that new here, except that we also said that an inductor looks like a short circuit for DC and an open circuit for AC. And a capacitor looks like a short circuit for AC and an open circuit for DC. Well, because once it fills up, it doesn't have anywhere to go. So what we're going to do is we're going to, let me bring up the whiteboard. Oh, come on, really? Video. Oops, I need to turn that off. No audio. Okay. I'm going to unshare this and I'm going to redraw it on my screen. And I know this is going to be about the end, so might go a couple of minutes over today. Yeah. Whiteboard. Make co-host. Okay. Okay, so here's our circuit. We have a capacitor, and we have an inductor, and we have our ground. And then this goes up to an antenna. Okay, so this
drew a line through your inductor this time.
I did. I could tap it. This would be continually variable. I could also draw it like it was like this. This would indicate a tapped inductor, where I basically would change the position and change the value. They effectively do the same thing.
Okay, so the original line is a tapped one and you drew an arrow instead.
Right. I just had it be continually variable, like a roller or something, like a coil, like a rolling coil. But it could be either one.
All right.
So, okay. So here is where this gets really interesting, because capacitors and inductors are kind of, if we look at them for pure AC or pure DC in their extreme, they get kind of dull because they're extreme, right? Okay, well, it turns out that we have this thing called resistance, okay? And does everyone remember what resistance is?
Opposes the current.
It opposes current. Well, in particular, resistance opposes something that opposes DC current. Resistance is the opposition to DC current. Well, there's also something called impedance.
Wait, when you're speaking of resistance, you're only referring to DC, and are you about to say that for AC you use impedance? Yep. Or what are you going to go ahead and say what you're going to say?
That's exactly right.
Oh, okay.
So our resistance is the opposition to DC current. Impedance is the opposition to AC current. So in a resistor, because it doesn't make any difference, it doesn't care, resistance and impedance are the exact same thing. And in fact, we're going to use Z instead. I want to use the letter Z. That's impedance. However, for an inductor or a capacitor, we already know that if we look at a piece of wire, our resistance is nothing. Does everyone agree with that? It's just a piece of wire. It's practically nothing. For a capacitor, what would our resistance be, considering it's just an empty space? Our resistance would be very high, right? So our resistance is 0 and our resistance is infinity for those things. But as it turns out, the impedance it is not zero, and the impedance is not infinity. Because AC, everything reacts differently. So in the extreme, we could actually say that the impedance is infinity. And we could say that for this, the impedance is equal to zero. But that's not complete. That's in the extreme. Well, in between the extremes, we have this other area. And this other area is where everything gets very, very, very useful. Because for a capacitor, we have our impedance is equal to negative 1 over 2 pi FC. And notice, what do we have in there? Remember that little letter F from yesterday? What's that letter F?
Frequency.
Frequency. And C is our capacitance. So that's Z of a capacitor. That's our impedance of a capacitor. Then we also have an inductor. Because the impedance of an inductor is 2 pi times, what's that little letter F?
Energy.
Frequency.
Oh, frequency.
And this should be an L, where the L is the inductor. So what does that mean for us, for practical terms? When we change our frequency, what happens to our values of impedance? If our frequency goes up, what happens to this one? Because it's in the denominator.
It goes down.
It goes down. If our frequency goes up, what happens to this one?
Goes up.
It goes up. Yeah, exactly. So
wait, can you say instead of this one, if frequency goes up, then what goes down?
Well, if frequency goes up, notice that the frequency is in the denominator of the capacitor one, and it's in the numerator, the top part of the inductor one. So basically, if frequency goes up, you'll see that this number becomes 1 over infinity eventually, which is 0. And this one will actually go to infinity. Well, that is the extreme case that we were talking about a little while ago. The same thing is if I have frequency going all the way to 0, 0 frequency would be DC. Well, if that's true, then this one goes to infinity and this one goes to 0.
Okay, again, this one, you're referring to the formula. But
Yeah.
could you just use simpler terms? What is it that goes up and down when the frequency goes up and down?
Okay, so let's ask this. If I just do this and say that it's equal to 1 divided by F, and this is equal to F, and I make F go to infinity, what's 1 divided by infinity? What's 1 divided by infinity, everybody?
0.
0. That's right.
You approach 0.
You approach 0. What happens if I have F and F is going up to infinity? What does the value become?
Infinity.
Infinity. If I have F going to 0 instead, which is going to DC, what is 1 divided by 0?
Infinity.
It's infinity. And what's 0? It's 0. Okay, so as these go up and down, notice that also they are also opposite signs. Notice there's a negative sign. There's no negative sign down here on the bottom. There's actually a positive sign. So at some point, what you're going to find is that these are equal and opposite. If they're equal and opposite and you add them together, what do you get? 0. Yeah, so you can set it up so that ZC plus CL is equal to 0. And the equation that you get is that F is equal to 1 over 2 pi square root of LC. I'm not going to do the math because that'll take a little too long. But This is the frequency at which these Z's become equal and opposite. So let me ask, if I have one of these followed by one of these, and these resistors, these values of Z add together and they're equal and opposite, what do they look like? They look like a straight wire. They have no impedance. If I were to actually plot this on a graph, what I would see is that my impedance at this point would go like this. And this would be known as resonance. We see this all the time. Do I determine what note this thing makes when I hit it? Or does it just make that note? Can everybody hear that?
No.
Basically that, when I hit my mug, it makes a note based on the size and shape of the mug. That is the resonant frequency of the mug if I put energy into it. If I pick a capacitor and an inductor and I build them into a circuit and make them equal by picking the L and the C, that will determine what my resonance frequency is. So now we go back to this circuit right here, which is the one that we drew. And notice that this is a capacitor and a capacitor and an inductor like this. And we have this in series with this. These add together. I have a ZC there and an antenna, which provides something. And then that in parallel, we're going to get to series and parallel tomorrow. And then that whole thing in series with this. So this is ZL and this is ZC. And what I can do is I can pick those so that I end up with a resonant circuit. So what you may say is the point of having that. The point of having that is that I can pick my components and I can adjust them using these knobs to make them behave in a different way. I can make this antenna, whatever the impedance is, look like something that I want it to look like. This is known as an antenna tuner. Or a match or an impedance matching circuit. And it is a very, very important circuit because it allows us to efficiently transfer power into an antenna and make it look like a different impedance that the radio is looking for. So,
is that useful for changing antennas, as far as like if you had a radio that wanted a certain impedance of antenna and you changed the antennas, you could adjust the way the receiver would view the antenna as far as impedance?
Exactly right. Equipment is designed for 50 ohms impedance. That is the impedance that the transmitter, that the radio's output and input are matched to. You match impedance so that you can maximize your power going across from one circuit to another. So let's say that I have an antenna system. The radio is looking for 50 ohms impedance. The cable is 50 ohm characteristic impedance. It's not actually a resistor. It just looks like a good match. If I have an antenna that's 50 ohms impedance, essentially the signal that I put out will go out and be radiated, and I will get nothing that comes back at all. If it, let's say, is 150 ohms impedance, it's 50 ohms here and 150 ohms there. Think about if you were to take a jump rope and tie it to a closed doorknob, like a door with a closed door, and you whip the jump rope. You make a wave that travels down the jump rope. What happens when it hits the door?
Reflex.
What does it do?
Reflex.
It reflects. That's right. Well, ideally, what if the jump rope were infinitely long? What would happen?
It would just stay going
It'd
forward. It
just
won't reflect.
go and it would go forever, right? So what we're looking for is an impedance match that would basically be the equivalent of a jump rope that went on forever. Well, we don't have that. We have this mismatch. It's tied to a doorknob, which means that our signal will go out and then some of it will be reflected back. Well, if some of it is reflected back, where does it end up?
In your outputs.
In your transmitter. That's right. Which, if your transmitter is operating at a voltage like this, because it is, and then another signal comes back that looks like this, what if they add together? Those are voltages. What would happen if they add together? You get this plus this. The result is way up here. What if your transmitter is not designed to handle a voltage like that? It can only handle a voltage this high. What will happen to your transmitter?
Can blow up.
You'll let the smoke out, as they say.
It goes to the shop.
That's right. It goes to the shop. Sometimes you can replace it and sometimes you can't. So that is why it's important to get an impedance match, which basically allows you to transfer power happily into a load, which is a device that's using your power. And that's why that little circuit, which looks like this, is so, so very important, because it allows you to essentially fool the transmitter into thinking that everything is hunky-dory in the real world. And what happens is the signal that comes out goes through this matching network, comes up to here. If anything gets reflected back, it gets to here and gets sent back up. And it will just basically go up and back and forth and back and forth and back and forth until there's nothing left, but it will never make it back into the transmitter. All right, any questions there? Don't be shy. I know this is a lot.
Does it bleed off some of that into the ground?
Some of it probably, yeah. Ideally, you don't want it to go to ground. You want it to reflect back and forth if you can. And eventually what will happen is the power will go somewhere. It will either go out the antenna or it will heat up your feed line, which is why now we get to questions of, okay, well, let's say that you have feed line, which has a certain amount of loss per 100 feet. That loss is measured in decibels. Depending on how lossy that feed line is will determine for if your match is really bad, you'll spend a lot of your energy just warming your feed line. If you have a really good match or very, very low loss feed line, you can get away with it. It's all a big game of balancing things. Any other questions, everybody?
Our manuals, Scott, don't show us those the neat math that you explained to us about relationships between capacitors and inductors.
No, I'm sure they don't.
Is there some place where we can go over that, like in a handout, or do you have some sort of handout that you could send to us?
I don't, but we might be able to find one. Like, might be able to find like a derivation. Let's see, derivation of resonant frequency in an RLC circuit. Let's see if this helps. Resonant frequency. Derivation of resonant frequency. There we go. Yeah. Sure. Series resonance and parallel resonance circuits. There we go.
Thank
you.
So
I will put that in the chat. All right. Any other questions? And don't be shy. By the way, you don't have to know that until at least the general class exam. So, which is another reason why, you know, if this is of interest to you, you've already been exposed to it. And if you feel comfortable with the technician stuff, why it's not a bad idea if you look at the general stuff and, you know, you understand the basic mathematics and things. There's a lot of overlap.
Did you send us a link for the recorded video from yesterday?
I did.
Okay. I get about 1,000 emails. I'll look through them.
All right. Any other questions, you guys?
Nope.
Okay. Just so you know, it gets easier now. we've gone through the hard math, and we've already done the electromagnetics, and we've already we have to do a little bit of series and parallel RLC circuits and things like that, but by and large, we're past all the hard stuff.
Okay, here's an easy question.
Yeah.
The material frequently uses the word station.
Yeah.
So is every ham operator with a little handheld transceiver a station?
The station, okay, so there's actually two parts to a license. There's an operator license and a station license. The station license is the equipment. The operator license is the license that goes with the person. So yeah, so basically any piece of equipment is a station.
Oh, the equipment is the station.
The equipment is the station. And the equipment, it's important to know, the station license carries no privileges with it. In other words, there's no inherent ability of that station to be allowed to transmit without somebody being in control of it who has privileges.
So
Have been granted to the manufacturer of the radio?
No, it's granted to the owner of the equipment.
so how does the station, how does the equipment get a license?
Basically, when you apply for a license, you're assumed to have a station license that goes with it. There's a station license and an operator license, and they're tied together. So basically, like if let's say we create a club, right? Let's say we create a club station. The club station has a station license, but no operator license because there's no operator per se. In other words, you can't just walk into a club station if you don't have a license and operate the club station. There has to be somebody who has been granted that. Now, there's an assumption that as an operator, you also have the ability to have a station. Your station license covers your equipment. So you have a station license, which covers your equipment, and an operator license, which gives you privileges.
If you get your license before you have a station, radio, whatever, you still get the station license. And then when you get your radio, you need to let them know?
It. No, that just becomes it. It's covered by it.
Okay.
Yeah, but that's why, let's say a club station has no privileges. It has a trustee who's responsible for it, but there are no inherent privileges assigned to it. You can't just take a club station and walk in without a license and use it. If you have a license, then whatever privileges you have transfer to the station.
Okay.
Frank, you're all muted, Frank.
Yeah. Hey.
I want you to say hi, Frank.
Hi, Frank.
Hey, Alex. I can't see you, Alex.
Come on, come on over here. Come here. She's a little shy and she's busy making a mess.
Well, Alex, you can't be shy and on the radio at the same time.
Yeah, she'll get over it.
Is Alex a cat or a dog or a snake?
No, Alex. How old is Alex, Frank?
She's an 11-year-old.
A boy? A human?
Oh, yeah, she. Yeah.
She.
Yeah, she's I think she's doing okay on assimilating, absorbing this, so.
Good. Hey, Alex, are you doing okay?
She says, mhm.
Are you studying hard?
Well, we got together quite a few times before we did this.
Yeah.
Most of what not today so much, most of yesterday we pretty much covered.
Hey, Toto, are you there?
I'm here.
How are you doing, Toto?
I'm doing good. Yeah.
Is this stuff like really hard, or are you getting
Well,
it?
I've actually covered all this in the book so far. So
Okay. And how old are you?
it's good. I'm 12 right now.
Okay, cool.
Yeah.
All right. Any words of advice?
Hey, 12.
He's 12. Yeah.
I don't know.
I want to hear the advice of youth.
The one by Roy Watson.
Yeah. All right. Anybody else with anything else?
Todd, I was just wondering, like I kind of heard like we are setting up a station somewhere. I did ask, but maybe I might have missed it again if you have said it. So I'm interested in helping out if at all it's somewhere around my place. So how can I help, or is it possible?
Where are you?
I'm in Portland downtown.
Okay, because we're down in Eugene. So.
Oh, okay.
But are you up at Portland State or somewhere around there?
Portland State. Yeah.
There's a club at Portland State.
I got to know about this class from Andrew from PSAS.
Yeah.
So, yeah.
Yeah, PSAS. We actually have had them come visit us during one of our club meetings down here. So I know that they've put up some CubeSats, and we're very, very curious about the CubeSats. So, but yeah, we're going to be building club stations down here. So, but I mean, we're 120 miles south. So,
yeah.
All right. Any other questions before we shut her down for the day?
Scott?
Yes.
Did I send you information about the in-person testing session that the Oregon Valley Club is doing Sunday, the first Sunday of the month? It'd be the second, I think.
I don't think so.
Hillsboro?
I don't think so.
Okay, I'll send you that, and you might, somebody who's up in Portland or the Hillsboro area might want to walk in and do the in-person test rather than online, or if your online is filled up. So it might be useful. I'll send it to you. Thanks.
Cool.
All right. Well, thank you.
Thank
Thanks,
you,
Scott.
everybody. We'll see you all tomorrow.
Okay.
And remember,
You guys.
you're halfway done, and you've done all the hard stuff.
Yay.
That's
Yay.
Haven't exactly done it. That's the problem.
Well, yeah, but
Think
go
about
do some practice.